iron core surrounded by a rocky mantle and a thin crust. The core of Venus, while not as well understood as that of Earth, is believed to be partially liquid, similar to Earth's. This iron core is estimated to be about 2,000 miles or 3,200 kilometers in diameter. Above the core lies Venus's mantle, composed of silicate rock that extends up to approximately 1,550 miles from the planet's center. This is overlaid by a thin crust estimated to be 6 to 12 miles thick. The rotation of Venus is a unique characteristic among the planets of our solar system. Unlike most other planets, which spin on their axes in the same direction that they orbit the Sun, Venus rotates in the opposite direction. This is a phenomenon that isn't yet fully understood by scientists, but some believe it may be due to a massive collision with a celestial body in the past, which altered the planet's rotational dynamics. Venus rotates extremely slowly, with a sidereal day, a full rotation on its axis, taking 243 Earth days, the slowest rotation of any planet in the solar system. This slow rotation contributes to the planet's lack of a significant magnetic field. Another quirk of Venus's rotation is that a solar day on Venus, the time from one sunrise to the next, is shorter than its sidereal day due to its retrograde rotation and orbit around the Sun. The solar day on Venus is about 116.75 Earth days. The planet's year, the time it takes to orbit the Sun, is about 225 Earth days, which is shorter than its sidereal day. This makes Venus one of the few planets where a day is longer than a year. The surface gravity on Venus is about 90% of the surface gravity on Earth. This means that if you were able to stand on Venus, you would feel slightly lighter than on Earth. However, the extreme atmospheric pressure and temperature would make it impossible for humans to survive without protection. Venus's surface appears to be geologically young, with a relatively low number of craters indicating a surface age between 300 million and 600 million years old. Scientists believe that Venus undergoes a cyclical process where heat from the planet's interior causes the surface to be repaved in a global resurfacing event. There is strong evidence of widespread volcanic activity on Venus. Thousands of volcanoes dot its surface, ranging from less than a mile in diameter to over 150 miles or 240 kilometers. The planet has far more volcanoes than any other in our solar system. However, there's currently no definitive evidence that these volcanoes are still active, although recent studies suggest that some may have erupted within the last few million years. Despite the apparent geological activity, Venus doesn't experience significant tectonic activity like Earth. While Venus does have mountain ranges and rift valleys similar to those seen in tectonically active regions on Earth, it lacks the kind of large, distinct tectonic plates seen on our home planet. This might be due to the planet's slow rotation, which limits the Coriolis effect necessary to drive large-scale tectonic activity. Venus's atmosphere is one of its most distinctive and intriguing characteristics. The atmosphere is primarily composed of carbon dioxide, 96.5%, with most of the remainder being nitrogen. However, there are also traces of other gases, such as sulfur dioxide, water vapor, carbon monoxide, argon, and helium. This composition is vastly different from Earth's nitrogen-oxygen atmosphere, making Venus's air toxic to humans and most known forms of life. The atmosphere of Venus is arranged in several layers. The troposphere, extending from the surface to about 40 miles up. The mesosphere, stretching from the top of the troposphere to about 56 miles high. And the thermosphere, which reaches up to 125 miles above the planet's surface. Above this, there's a transitional region called the exosphere that merges with the void of space. The high concentration of carbon dioxide in Venus's atmosphere creates a strong greenhouse effect, trapping heat and making it the hottest planet in the solar system, even hotter than Mercury, which is closer to the Sun. The greenhouse gases in the atmosphere absorb heat energy radiated from the Sun, preventing it from escaping back into space. This results in surface temperatures averaging around 467 degrees Celsius, which is hot enough to melt lead. There's very little temperature variation between day and night or between the equator and the poles, due to the thick atmosphere's efficient heat distribution. This results in a virtually constant, furnace-like temperature all over the planet's surface. The atmospheric pressure on Venus is enormous, approximately 92 times greater than Earth's at sea level. This is equivalent to the pressure experienced 0.62 miles deep in Earth's oceans. A human exposed to such pressure without protection would be crushed. Despite this, high up in Venus's atmosphere, approximately 31 miles above the surface, the pressure and temperature conditions are similar to those on Earth's surface. Venus's atmosphere is perpetually cloaked in thick, opaque clouds that cover the entire planet. These clouds reflect about 75% of the sunlight that reaches Venus back into space, which is why Venus is so bright and easily visible from Earth. The winds in Venus's upper atmosphere are incredibly fast, reaching speeds up to 450 miles per hour, much faster than the strongest hurricane winds on Earth. These winds move in a phenomenon known as superrotation, where the atmosphere rotates much faster than the planet's surface. Near the surface, however, winds are much slower, typically less than a few miles per hour. Venus boasts the highest mountain in the solar system, Maxima Montes, rising 20 kilometers, about 12 miles above Venus's mean surface level. The planet's surface is also marked by numerous impact craters, extensive lava flows, and unique surface features like coronae, circular structures caused by the upwelling of hot material from the mantle and arachnoids, circular structures with a complex pattern of fractures. Due to Venus's slow rotation and dense atmosphere, the planet doesn't experience significant seismic activity like Earth. However, recent studies suggest that Venus may still be geologically active. Venus has been a target of interest since the dawn of space exploration. The Soviet Union's Venera and Vega missions, NASA's Pioneer Venus, and the European Space Agency's Venus Express have all contributed significantly to our understanding of the planet. The Venera program achieved many firsts, including the first human-made device to enter the atmosphere of another planet, and the first successful landing on another planet. These missions provided valuable data on Venus's atmosphere and surface. More recently, NASA's Magellan orbiter mapped almost the entire surface of Venus using radar to penetrate the thick cloud cover. This mission revealed details about Venus's surface features and geology. Despite the challenges posed by Venus's harsh conditions, scientists are interested in further exploring the planet. NASA's planned Veritas and Da Vinci Plus missions aim to study Venus's geologic history and atmospheric conditions, providing insights into whether Venus might have once harbored liquid water or even life. Meanwhile, the European Space Agency's Envision mission will focus on understanding why Venus and Earth took such different evolutionary paths. Japan's Akatsuki mission is currently studying Venus's atmosphere and weather patterns. Venus, our neighboring planet, is an intriguing world of extremes. Its harsh environment poses significant challenges to exploration, yet its similarity to Earth in size and composition, along with hints of potential past water and geologic activity, keep our curiosity alive. As we prepare for new missions to Venus, we stand on the brink of major discoveries that could reshape our understanding of the solar system and our place in it. As a reflection on our own planet's potential future, Venus serves as both a warning and an opportunity for scientific discovery. Space has always captured humanity's collective imagination. Among the pantheon of celestial bodies that have fascinated us, Jupiter stands out as the largest planet in our solar system, its vibrant stripes and prominent great red spot making it easily recognizable. But there's far more to Jupiter than its size and famous storm, and our knowledge has grown exponentially with advancements in space technology and exploration. Jupiter is a gas giant consisting mostly of hydrogen and helium. Its diameter is approximately 11 times that of Earth, and it's so large that over 1,300 Earths could fit inside it. Despite its size, Jupiter has the shortest day of all the planets, rotating on its axis every 9.9 hours. Jupiter's magnetic field is the strongest of any planet in the solar system, created by electrical currents driven by its fast rotation and the movement of metallic hydrogen within its outer core. Jupiter's famous bands are actually high-pressure zones, characterized by lighter-colored clouds. Conversely, its darker regions are low-pressure zones. The vibrant colors we see are due to different types of clouds. Ammonia crystals create the white bands, while other chemicals produce the reddish, brownish, and yellowish hues. As for the Great Red Spot, this iconic feature is a persistent high-pressure region in the atmosphere, resulting in a storm that's been ongoing for at least 300 years. The Great Red Spot is one of the most recognizable features of Jupiter, the largest planet in our solar system. At its widest point, it stretches 1.3 times the diameter of Earth, although its size varies over time. Notably, it has been shrinking in recent decades. The storm has been continuously observed since the late 19th century, but historical records suggest its existence for at least 300 years. The Great Red Spot is located in Jupiter's southern hemisphere, nestled within a westward-moving jet stream called the South Equatorial Belt. The red color of the Great Red Spot is still a subject of research. It's thought that the color may come from complex organic molecules, red phosphorus, or possibly compounds containing sulfur. The exact chemical reactions that give the spot its vivid color remain a mystery. The storm rotates counterclockwise with a period of about 6 days. Interestingly, the rotation speed, size, and color of the spot can change, reflecting the storm's complex interaction with its surroundings. The longevity of the Great Red Spot is intriguing. While storms on Earth last for days or weeks at most, the Great Red Spot has persisted for centuries. This longevity is likely due to Jupiter's rapid rotation and lack of a solid surface, which minimizes frictional dissipation of the storm's energy. The Great Red Spot is a window into the atmospheric dynamics of Jupiter, a gas giant with conditions vastly different from our home planet. Understanding this celestial maelstrom not only unravels the secrets of Jupiter, but also sheds light on the broader principles governing atmospheres, including our own. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who discovered them in 1610. Each of these moons is a world unto itself. Io is the most volcanically active body in the solar system, its surface covered in sulfur and sulfur dioxide, giving it a colorful, mottled appearance. Europa has a crust of ice, and scientists believe it might harbor a subsurface ocean, making it a potential site for extraterrestrial life. Ganymede The largest moon in the solar system is the only moon known to have its own magnetic field. Callisto, characterized by an extremely cratered surface, is believed to have an ocean beneath its surface as well. As of my knowledge, cut off in September 2021, Jupiter was known to have 79 moons, but additional moons may have been discovered since then. Saturn isn't the only planet with a ring system. Although much fainter and smaller, Jupiter also has rings composed mainly of dust particles from impacts on the planet's small innermost moons. These rings were first discovered by NASA's Voyager 1 spacecraft in 1979. The study of Jupiter has come a long way since Galileo's first observations. Multiple missions, such as Pioneer 10 and 11, Voyager 1 and 2, Galileo, Juno, and more, have been sent to Jupiter to study its composition, magnetic field, and moons. Pioneer 10 and 11 were the first spacecraft to make a close approach to Jupiter, providing valuable data about its radiation belts, magnetic field, and some moons. Voyager 1 and 2 made significant discoveries, such as detecting Jupiter's rings and confirming Io's volcanic activity. The Galileo orbiter spent 8 years studying the planet and its moons, and the attached probe made a direct plunge into Jupiter's atmosphere, providing the first direct measurements of its composition. The Juno mission, still ongoing as of 2021, has made significant contributions to our understanding of Jupiter's internal structure, atmosphere, and magnosphere. Jupiter, the colossal gas giant, remains a focal point of curiosity for astronomers and space enthusiasts alike. Its impressive size, complex atmospheric dynamics, multitude of moons, and faint ring system make it a fascinating object of study. As we continue to explore Jupiter through telescopic observations and space missions, we unravel the secrets it holds, enriching our understanding of the cosmos. For now, we marvel at the celestial symphony Jupiter conducts, its presence a testament to the intricate, diverse, and vast nature of our solar system. Ladies and gentlemen, welcome to today's topic, aliens. Are they real? Do they exist? And if so, what do they look like? Today we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Here are a few theories about aliens. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars, or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy, or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. That's all for today's topic of aliens. We hope you've enjoyed this discussion and learned something new. If you have any questions or comments, please leave them in the comment section below. Thanks for tuning in, and we'll see you next time. Nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space. from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch. The subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms. Protons and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost 1 billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars in all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe and the strange and surreal paradoxes in what we think we understand. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Everything we know represents just 5% of the universe. What is the rest? Normal matter, protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, Scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in space-time. This is known as the 4-dimensional space-time. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature? In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us, but why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics, as we know them, break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in spacetime. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us onto new and unexpected ways, spurring us onto new heights of discovery and understanding. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. This is the Milky Way, our galaxy. Approximately 12 billion years old, the galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars first and foremost. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years. This is how far light can travel in a year. Our galaxy's diameter is over 100,000 light years, and we're now located at a distance of 25,000 from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our own cosmic backyard and much bigger than Andromeda. But M87 is tiny compared to this giant. 6 million light-years across, IC1011 is the biggest galaxy ever found. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous, but why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.7 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time. So galaxies must have come from that very early universe and formed from it. For stars to form, and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together because to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble, the light we see from distant galaxies now. However, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots. They are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust, gas, and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source. And our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars, as far as we can tell. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations, like the Whirlpool galaxy, then over billions of years develop into more orderly forms. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior. And they found out: a black hole. And not just any kind of black hole, but it's a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings, much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the sun, the stars also move due of gravity. What we discovered was a bizarre and violent environment. At the center of our galaxy, everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. So, is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light years. That's many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. So what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was at action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, He deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, and that's why he graded on the astronomical community. And this is a brilliant idea. But he was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it. You can't feel it. However, it is likely everywhere. It's a ghost-like material that will pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. And the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true, they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters, containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The 2 galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda, and that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda, as we know it, will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide. But this age of galactic cannibalism will eventually pass, because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there, there aren't as many stars. we might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities. We used to only know about the planets that circled around our sun. But now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun's system. But now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which has 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope out into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, they have found more than 400. Some are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are huge, rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star they're burning up. One thing is clear. No 2 planets are the same. Each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So, at the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with a cake. Then you'd put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way, depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in, it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids, and these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across. Then, it has enough gravity to crush it into a sphere. Any smaller, and it stays in irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things, like most metals, fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now, they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, They sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense. So, it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else, which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust, and that crust started to build up again in the south of Mars. There were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal, rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials. But each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. And that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye, and you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between 2 moon missions that would have killed the astronauts if they were there. So, radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens. As the Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then, big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry and there's not much going on. So why have the 2 planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only the atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So, not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field. And it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. And that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop. The flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere and the water evaporated. Mars turned into a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water, frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big. Because there was so much ice and gas, their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality, they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons. Some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside, far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995, Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachute slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they're so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by a very hot liquid metal that spins around the planet's solid iron core. Most likely, gas planets do about the same thing. But gas planets don't have iron cores that get very hot. They formed around frozen cores of dust and ice. So we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior. So, it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the Sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us, Homo sapiens, to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there, that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So, water is everywhere in the universe, and we're finding that planets are too. But we haven't yet found another planet where water is liquid. More than 400 new planets have been found by scientists. Our world doesn't look like any of them. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. So, it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. We know that our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain: there are billions of planets out there waiting to be discovered. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that when miners in the Rockies came out of their tunnels, they thought the sun was coming up. So bright, in fact, that even at midnight you could read a newspaper. It didn't just happen in the US. People all over the world saw these auroras. No one knew why they had happened. But earlier that same day, an astronomer had seen something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed to have nothing to do with each other. But we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. And if this violent event happens again, it could destroy our modern technological world. The sun is the most familiar thing in the sky. It gives all life on Earth heat and light. It is so big that it's hard to imagine, and it makes up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and was made by the burning of hydrogen and helium for the last 5 billion years. But from an astronomical point of view, it's nothing special. A G main sequence star, also known as a yellow dwarf. But looks don't always tell the whole story. Solar flares and explosions of plasma, particles, and radiation from its surface travel far into space. We call this process the solar wind. Solar storms, on the other hand, are very violent eruptions. And a coronal mass ejection, or CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, we'll find out how bad a CME could be and what astronomers are doing to keep an eye on our star to try to predict when they might happen. Step back in time to 1859. First, in Victorian Britain, it was okay for a gentleman to be interested in solar astronomy. And one man did it in a very good way, Carrington Richard Christopher. We don't know what he looked like, though, because there are no known portraits of him. Carrington learned many important things from what he saw. He saw that different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body, but a fluid one. But he also saw that sunspots could be the start of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky in the morning. So Carrington was doing what he always did, which was to look for sunspots. He was using his telescope to project an image onto a screen. At 11:18, he saw two brilliant beads of blinding white light appear in what Carrington calls a kind of conflagration. Stranger still, they were gone after 5 minutes for no clear reason. Carrington had seen a coronal mass ejection, which was a huge magnetic explosion. A huge cloud of charged particles that are thrown off the sun's surface. After 18 hours, the Earth was hit by an electromagnetic storm. People started calling it the Carrington event. At the time, everyone was talking about the beautiful aurora, which could be seen all over the world. Even though a few telegraph systems went a little crazy because of power surges, it didn't have much of an effect on everyday life. Don't forget, though, that this was 20 years before the light bulb was made. That was in the past. Things would be very different right now. Coronal mass ejections are common, but they can be different sizes and move in different directions. So, the question is, what are the chances that something like what happened in Carrington will happen today? And how would it change things? So, what is going on at the sun, on the surface of the sun, when we talk about the solar wind and space weather? The sun is made of magnetic fluid, and when that magnetic fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, which are called mass ejections. And these explosions are huge, sending out 1 billion tons of material at 1 million miles per hour. So, we want to know where these things are going, because if they move toward Earth, they could affect the technologies we use. There's a very famous event in Quebec in 1989 where some power systems were disrupted for many hours in October. We've heard about the Carrington event, which happened in the 1800s. What would happen if it happened today, and how would it affect us? If we think about what we use satellites for now, we have GPS spacecraft that help us find our way, communication satellites, weather satellites, and even the stock markets are linked in some way. But we also have bigger power grids and a lot of wireless technology, and we don't know how they will react. How likely is it that something like the Carrington event could happen again? We know that the sun can still make these things happen. In 2012, there was an event that luckily didn't come toward Earth, but it did pass over one of the spacecraft we use to watch the solar wind. And it pushed all the sensors on that spaceship to their limits. So from what we've learned, we think that was at least as powerful as the Carrington event, and maybe even more so. It's just a coincidence that a big CME and one that's headed toward Earth both happened at the same time. And that's mostly just a matter of luck. We either get one or we don't. And how do we do with making predictions? Can we predict what the sun will do in a week, a month, or a year? Once a CME is up and running, we can start making predictions so that we can figure out how big it is, how fast it's moving, and most importantly, where it's going. All of this sounds very scary. Space weather is a problem, and the UK government knows this. The National Risk Register lists it. It's about as bad as a pandemic of flu. So, the people who make spacecraft are trying to find out what the most extreme conditions are in space, so they can make them so that they can handle those conditions to a certain degree. Both NASA and ESA are getting ready to send satellites into space that will get closer to the sun than ever before. The MET office's Space Weather Operations Center opened in 2014. It is one of only 3 places in the world that can predict the sun's effects on Earth around the clock. So far, the sun has had almost no sunspots, and the side that faces Earth is not expected to have any more sunspots or CMEs that are important. So luckily, there isn't much going on right now, and things don't look too different in the long run. So, spacecraft, satellites, power supplies should be safe for the foreseeable future. Trouble is, the foreseeable future in space weather forecast is, at most, just a few days. We still don't know a lot about CMEs, like where they're going, how big they are, or when they might happen in the future. 2 new solar probes will get closer to the sun than any other spacecraft has ever done. The Parker Solar Probe was supposed to be sent into space, and its destination will be close enough to the sun's surface to fly through the source of the most energetic solar particles. The Parker Solar Probe is an exploration mission that will measure the gas and magnetic field near the sun to figure out why this stuff is spreading out into the rest of the solar system. And this, the Solar Orbiter from ESA. Solar Orbiter might find out how sunspots, flares, and coronal mass ejections on the sun's surface are related to the solar wind. Solar Orbiter's success will be very important for our understanding of how the sun works. We think that the sun's magnetic field is made in a way similar to how Earth's is, but it is much more dynamic and changes all the time. We have an 11-year sunspot cycle, during which the sun's magnetic fields move towards the poles and the polarity changes. On top of that, the magnetic field goes out into the solar system and flows over all of the planets. Solar Orbiter will measure these magnetic fields for the first time, and it will also give us the chance to watch the magnetic fields move to the sun's poles. To do this, Solar Orbiter will take pictures of the sun's atmosphere and measure the number, speed, and temperature of the particles moving across the space between the sun and Earth. But the magnetometer, which is made to measure the tiny magnetic fields in space that are carried by the solar wind, could be one of the most important and sensitive instruments. The sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, who was the first person to record ACME, it was just a strange event. But now we know that these things can do a lot of damage to the world we live in. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejection will happen.
The crater counting techniques developed from our exploration of the Moon allow us to place our observations of Mars today in historical context. They allow us to construct an absolute timeline. If we see evidence that water once flowed across a surface or pooled within a crater, and we can date the area using crater counting, then we can estimate when the water flowed and when it disappeared. As we've discussed, Curiosity is exploring Gale and painting a vivid picture of what happened there. Crater counting allows for an estimate of when, independent from the rover's ground-based measurements. A recent analysis using images from orbit taken by MRO found 375 craters ranging in size from 88 meters to 23 kilometers inside Gale crater, implying an age of 3.61 billion years, with an uncertainty of around 60 million years. This places the formation of the crater and the geological events that played out inside it during the late Noachian, early Hesperian, and this time frame is consistent with observations of the presence of water at many other sites of a similar age. Consistency over a wide range of independent observations is extremely important in science. One site or set of observations alone may be tantalizing, but rarely compelling. Multiple independent observations reduce the uncertainty and give scientists more confidence in their understanding. When our goal is to understand the sequence of events on an ancient landscape far away that no human has ever visited, caution and consistency are both vital commodities. Since we have only one active rover at present, and landings are by their nature rare and confined to limited geographical regions, orbital observations of much wider areas of the planet are a vital tool. MRO's high-rise camera has provided some of the most beautiful and detailed high-resolution photographs in the history of space exploration, covering over 99% of the Martian surface. Features as small as a meter wide can be seen in these images, and the camera can also operate in the infrared, allowing for the identification of different minerals at the surface. There are many beautiful photographs in the MRO library that reveal evidence of persistent lakes and river systems, particularly across the Noachian terrain in the southern highlands. Sites such as the Jezero crater clearly show meandering river channels draining into deltas. Some images, constructed using both visible light and data from the spacecraft spectrometer, reveal well-defined river channels flowing out of the crater and the presence of carbonates and clays that form where there is persistent liquid water. For these reasons, the Jezero crater is one of the 3 prime targets for NASA's Mars 2020 rover. Some of the more recent finds are associated with the Arabia Terra region, which sits between the Noachian southern highlands and the great lowlands of the north, where water could have flowed towards a possible northern ocean. Researchers from University College London and the Open University studied an area of Arabia Terra equivalent to the size of Brazil, using high-resolution imagery from MRO. The study mapped a network of over 17,000 kilometers of ancient river channels, not the usual excavated dry river valleys, but rather a network of inverted channels, raised lines of sand and gravel laid down on the riverbeds, that persisted while the land around them eroded away long after the rivers dried. Similar ghost rivers are seen in desert environments on Earth in Utah, Oman, and Egypt, where erosion rates are slow. The identification of the ghost rivers allows for Arabia Terra to be identified as a fossilized floodplain, somewhat like the lower sections of the river Ganges on Earth, the lowland interface between mountain rivers and the sea. This is an important discovery because it feeds into a long-standing and still unresolved scientific debate about the nature of the Noachian climate. Nobody disputes that rivers once flowed on Mars, or that many impact craters were once home to lakes. The key question is one of longevity. Was Mars warm and wet for long periods of time, or was it for the most part a frozen planet on which water occasionally melted, perhaps triggered by sporadic volcanic activity or shifts in the planet's orbit? The tension arises because climate modelers find it very difficult to simulate an ancient Martian atmosphere thick enough to deliver a stable climate over hundreds of millions of years that would have been lost at a sufficiently fast rate to produce the Mars we see today. In a recent review, for example, Robin Wordsworth concludes, "The weight of geochemical and geomorphological evidence points towards a late Noachian hydrological cycle that was intermittent, not permanently active. And the latest state-of-the-art Martian climate simulations suggest a water-limited early Mars with episodic melting episodes may be a suitable paradigm for much of the later Noachian and early Hesperian climate." Before the recent analysis of the Mars Global Surveyor data, it was thought that there was a relative absence of river channels on Arabia Terra, and this was interpreted as support for a frozen, episodically wet Mars. Ice may have been concentrated in the southern highlands, and so lower elevations like Arabia Terra may have been generally more arid and therefore devoid of river channels. This appears not to be the case. Arabia Terra was once very wet indeed. This debate has no consensus resolution at the time of writing, which reminds us of important points about both our knowledge of Mars and science in general. We are describing and attempting to understand and contextualize events that happened over 3.5 billion years ago, at or around the time that life on Earth began. That is an immense span of time, during which orbital parameters have changed, solar output has varied, and innumerable impact events have cratered the planets. Tracing the evolution of an atmosphere backwards through time from today's measurements, anchored by geological and geochemical evidence from a few landing sites and orbital imagery, is extremely difficult. Suffice to say, there remains an unresolved tension between Mars's small size and large distance from the Sun, and the clear evidence of an ancient water cycle, episodic or persistent. As Wordsworth writes in the introduction to his review, the nature of the early Martian climate is one of the major unanswered questions of planetary science. The complexity and apparent intractability of the mystery is reason enough for many scientists to study Mars. The character of the scientist requires not only comfort with, but attraction to the unknown, an acceptance of and delight in the complexity of nature. There is no simple story of any planet. They are each too big and too old and subject to too many variables. We might reflect on what that means for our own existence, as individuals and as a species. The specific fact of our existence is inextricably linked with the evolution of our planet through an incomprehensible web of cause and effect stretching back via major and minor events, many beyond Earth itself, and filtered by the multidimensional sieve of evolution by natural selection. This connects us with every living thing that went before, back to the origin of life almost 4 billion years ago, and the origin of our planet 500 million years before that, and the origin of the solar system and the laws of nature who knows when, perhaps during the Big Bang, or perhaps infinitely far away in time. There's a lot we can't know. The search for certainty is a fool's errand, and the lesson is to find delight in not knowing, while simultaneously committing to extending the domain of the known. That's the key to science, the key to happiness, and the only reasonable response to the existential challenge of existence, because it is the truth. If you don't like that, comfort yourself with the fact that the domain of the knowable is vast, possibly infinite, and perhaps paradoxically, the knowable things about Mars may exceed those about Earth. Because Mars has been in deep geological freeze for much of its life, it is easier to research the deep past than it is on Earth. And that deep past may include the origin of life. Traces of the geochemical alchemy that led to the emergence of self-replicating, information-carrying carbon molecules on Earth 4 billion years ago weathered away long ago, although clues may be found in the common structures and chemistry of living things today. On Mars, however, geochemistry was frozen and archived in regions such as Arabia Terra. If, therefore, life began or even still exists subsurface on Mars, such a discovery may deliver insight into our own origins that would simply not be possible by studying the weathered, ever-changing ecosystems of Earth. This may be the gift of unknowable Mars. She's less unknowable than Earth. The Eridania region of the Southern Highlands may provide the most compelling evidence yet of a warm, wet, early Mars, with conditions not dissimilar to Earth at the time when life began. The analysis we describe below is a beautiful example of how the suite of science instruments aboard multiple spacecraft in orbit around Mars can be combined with our knowledge of cratering rates on the Moon to characterize an environment and trace its history back through deep time. It is also a beautiful example of the interconnected nature of science and the value of exploration. We've already met the elevation maps from the MOLA aboard the Mars Global Surveyor. This topological data, in concert with visual data from MRO revealing the location of valley networks, suggests that the Eridania Basin was once a giant lake, possibly the largest ever to exist on Mars, 1.5 kilometers deep in places, and containing 3 times more water by volume than the Caspian Sea on Earth. We know the terrain is late Noachian, around 3.7 billion years old, from crater counting. The CRISM spectrometer on board MRO reveals the mineralogical composition of different areas of the Eridania Basin, and this can be used in conjunction with the topological and visual data to build a 3-dimensional picture of the landscape and its chemical composition. In the deepest areas of the Eridania Basin, magnesium and iron-rich clay minerals are common, laid down as sheets of saponite, talc, serpentine, and so-called tot clays. These are characteristic of seafloor environments on Earth. Materials known as iron-rich phyllosilicates are also seen, which are again characteristic of terrestrial seafloor deposits. The mineral jarosite is detected, suggestive of the chemical weathering of sulfite deposits. There are many different carbonate signatures containing iron, manganese, magnesium, and calcium. Higher up the basin walls, chlorides are found, which are indicative of evaporation in shallower water. The most likely explanation for the origin of the deep clay, carbonate, and sulfite deposits, it's argued, is volcanic activity on the floor of a deep lake, because very similar deposits are seen at hydrothermal sites on Earth. The iron minerals detected are similar to those formed in the iron-rich early oceans of Earth, prior to the release of large amounts of oxygen into our atmosphere by photosynthesis. All this beautiful topological, visual, geophysical, and geochemical data can be combined to produce a picture of what was happening in the Eridania Basin around 3.7 billion years ago. The geochemistry of the low-lying regions is indicative of a deep-sea, volcanically active hydrothermal environment, with the salt-rich deposits at higher elevations suggestive of slow evaporation in shallower waters. The basin contained an iron and mineral-rich ocean, energized by active volcanism deep below the waves. A cauldron of complex geochemistry, stirred by the constant flow of energy from the inner planet. This is a striking conclusion because at the same time a few 100 million kilometers across the solar system on Earth, many biologists believe that life began in similar deep-sea volcanic environments. The theory that life on Earth began in hydrothermal vent systems is mainstream, although not universally accepted by any means. The idea is partly based on the observation that all living organisms on Earth today share a chemistry associated with the establishment of gradients in the concentration of protons across membranes, known as chemiosmosis. Proton gradients are also characteristic of the geochemistry of alkaline hydrothermal vent systems in acid oceans, which were common on the young Earth and perhaps the young Mars. An analysis published in 2017 claims to have detected evidence of biological activity in rocks laid down by hydrothermal activity at least 3.77 billion years ago in the Nouveau-Guittouk crustal belt in Quebec, near the Greenland Ishua rocks. The evidence comes from tube-like coils of the iron oxide mineral hematite, similar in size and form to structures laid down by iron-oxidizing bacteria in hydrothermal environments today. It's possible that the rocks at Nouveau-Guittouk are much older. A radiometric date using the samarium-neodymium decay process suggests an age of 4.28 billion years, which would make them by far the oldest rocks on Earth, and an astonishingly early date for biological activity. These findings are controversial, in part because of the difficulty of understanding how Earth's active geology has modified the samples over such vast timescales. This is where Mars may have an advantage over Earth in helping us to understand the processes by which the chemistry of a planet became the chemistry of life. The environment at Eridania is far better preserved than that at Nouveau-Guittouk. It has been in sterile, almost deep freeze conditions for over 3 billion years, the ultimate laboratory for studying the origin of life, if indeed life began on Mars. The story of the Eridania Basin and the possible scientific promise it holds was pieced together by using the results from different instruments on different spacecraft over many years, spanning several scientific disciplines: geology, chemistry, spectroscopy, laser altitude ranging, and photography. The estimate of the age of the surface required the Apollo lunar rock samples from 50 years ago, and radiometric dating techniques which required an understanding of nuclear physics. The estimate of the age of the surface requires a model of the entire solar system in order to interpret the measured crater density, which illustrates another important idea. The solar system is a system. No planet is an island. No planet can be understood in isolation, just as the structure of any one living thing on Earth cannot be understood in isolation. Organisms are a product of evolution by natural selection, the interaction of the expression of genetic mutations and mixing with other organisms in the ecosystem and the wider environment. The planets formed in a chaotic maelstrom from motions as random as the impact of a cosmic ray on a strand of primordial DNA. And whatever worlds emerged from the chaos have had their histories shaped profoundly by their mutual interactions throughout their evolution. The late heavy bombardment is a beautiful example. If indeed we discover that life began in the Eridania Basin, what a magnificent illustration of the unity of knowledge that would be. Understanding developed over centuries, the life's work of thousands of explorers, field geologists, chemists, biologists, astronauts, engineers, distilled into the discovery of a second Genesis. But more than that, because of the pristine nature of the ancient environments on Mars, such a discovery would deliver an insight into our own origins that may not be available to us here on Earth. Mars is a time capsule, containing the frozen chemistry of an ancient world similar to the Earth when life began. But while Earth's deep past has been largely erased by 4 billion years of geology and the action of a complex global living ecosystem, which has transformed the planet and its atmosphere beyond all recognition, Mars is a fossil from the deep past. This raises the wonderful possibility that another world, albeit an integral part of our system, may be the key to decoding the mystery of the origin of life here, the reason we exist. It's almost as if we have to leave the cradle in order to truly understand it. Around 3.5 billion years ago, change was underway on Mars. The warmer, wetter episodes that characterized the planet for millions of years during the Noachian became less frequent, and the climate drifted, imperceptibly at first, towards the colder, arid state we recognize today. The water that flowed freely over the surface during the Noachian became locked away in giant reservoirs of ice. Lakes turned solid, and rivers ran dry. The planet wasn't dying, far from it. The fireworks of the late heavy bombardment had faded, but rumbles from the deep maintained the violence. The shield volcanoes of Tharsis, including the mighty Olympus Mons, continued to build even as global temperatures plummeted, and subsurface lava flows occasionally melted the reservoirs of ice, leading to catastrophic floods that challenged the imagination in their scale and violence. The age of Noah became the Hesperian, the age of floods, or rather less portentously and more accurately, the age of occasional floods. The Hesperian period is named after the Hesperia Planum, a giant lava field to the northeast of the Hellas Basin in the southern highlands. The plain was resurfaced partly by the volcano at its center, Tyrrhenus Mons, and spans almost 2 million square kilometers. First photographed by Mariner 9 in 1972, it's a relatively flat landscape with few visible rock formations. The most prominent surface features are the craters that allow us to date it. Tyrrhenus Mons is a very different volcano to Olympus Mons and the giants of Tharsis. It's much more ancient, fully formed not long after the Hellas impact 4 billion years ago, and it erupted through water or frozen ground, a process that produces large amounts of ash rather than lava, what geologists call a pyroclastic eruption. As a result of its age and composition, Tyrrhenus was more prone to erosion than the giants of Tharsis, and today stands only 1.8 kilometers above Hesperia Planum. The Hesperian period was coincident with increased volcanic activity, particularly at Tharsis. But there's not necessarily a causal link between volcanic activity and the transition from the Noachian to the Hesperian. What is clear is that volcanism became the dominant geological force on Mars as the long-lived water cycles waned and cratering rates declined after the late heavy bombardment around 3.5 billion years ago. This is seen in both surface features and mineralogy. Hesperian surfaces are richer in sulfates rather than the clays and carbonates of the Noachian. Sulfates form in the more acidic atmospheric conditions created by the release of sulfur dioxide from volcanoes. While volcanic activity was the dominant force sculpting the smoother Hesperian landscapes, there are spectacular and notable exceptions where water reasserted its dominance, if only for a moment. Ekus Chasma is an unremarkable valley today. Images taken by MRO reveal a deep, steep-sided depression lying to the north of the Mariner Valley. At 100 kilometers long, 10 kilometers wide, and between 1 and 4 kilometers deep, it would be impressive on Earth, but is dwarfed by the magnificent neighboring valley system. 3.5 billion years ago, on frozen Hesperian Mars, however, things were different. High above, on the Tharsis Rise, lava surged upwards through the crust and met great reservoirs of ancient ice, releasing vast amounts of water that raged down from the southern highlands. The meltwater was funneled towards Ekus Chasma, where it created one of the briefest and yet most spectacular wonders of the solar system. The waters from the highlands came tumbling over the cliffs, roaring 4 kilometers down into the valley below, over the largest known waterfall in the history of the solar system. Around 350,000 cubic kilometers of water cascaded through the valley, the equivalent of a cube 70 by 70 by 70 kilometers, in less than 2 weeks. This being Hesperian Mars, the atmosphere was not substantial enough for the liquid to persist on the surface, and the water disappeared as quickly as it came, leaving scant evidence of the great falls etched into the canyon walls. Ekus Chasma was unique in scale. But the cycle of volcanic eruption followed by fleeting catastrophic floods was repeated in many locations across the planet throughout the Hesperian. However, in the thinning atmosphere, the presence of liquid water was probably always fleeting, increasingly so as time passed. Hesperian became Amazonian around 3 billion years ago, plus or minus 500 million years or so. When a Mars expert is asked the question, when did the Amazonian begin, they will usually say, depends who you ask. But certainly by 2 billion years ago, long before there was complex multicellular life on Earth, Mars was pretty much indistinguishable from the planet we see today. The red planet didn't die entirely. Volcanic eruptions persisted and have occurred in the very recent past at Tharsis. There may yet be eruptions in the future. But we do know that Mars changed from a world that supported liquid water on the surface under a thick atmosphere, via a period dominated by intense volcanic activity and episodic floods, into a hyper-arid frozen planet with a tenuous atmosphere, more befitting its small size and place in the solar system. This drama played out very roughly during the first 1.5 billion years of its life. The challenge is to understand why. Losing atmosphere. The climate of a rocky planet is a complex dynamic system shaped by myriad interactions, feedbacks, and instabilities, and inevitably changes over geological timescales. The thin envelope of atmospheric gases can be affected dramatically by volcanic and tectonic activity and impacts from space, and on longer timescales by shifts in orbit and tilt, and changes in solar output. Earth seems to be a remarkable exception. The most dramatic atmospheric change over the last 3 billion years has been the gentle introduction of oxygen by photosynthesis. Mars today has a thin atmosphere composed primarily of carbon dioxide. We know this atmosphere must have been significantly thicker in the past, quite possibly at an even higher pressure than that of modern-day Earth, because there was once liquid water on the surface. Mars must therefore have lost most of its original atmosphere, and it's important to understand where it went and why. The ancient atmospheric carbon dioxide molecules could have frozen out onto the surface in the polar ice caps, become locked away in the subsurface as carbonate minerals, or they could have been lost to space, or some combination of all three. To measure the composition of the Martian atmosphere today and understand how it evolved over time, a dedicated mission arrived in orbit in September 2014. MAVEN, the Mars Atmosphere and Volatile Evolution mission, has no high-definition cameras and provides no dramatic photographs of the surface, because the questions MAVEN was designed to answer are about the invisible envelope of gases surrounding the planet. If curiosity is the extension of our hands and MRO our eyes, MAVEN is our nose, sniffing the air for clues to the past. The spacecraft operates in a highly elliptical orbit, bringing it as close as 150 kilometers above the surface and out beyond 6,000 kilometers. This eccentric path means that on every orbit, MAVEN experiences a wide profile of the Martian upper atmosphere, allowing it to build a three-dimensional picture of the gases that still remain and how their distribution changes with altitude and time. MAVEN's measurements show that Mars is losing atmospheric gases today at a rate of about 2 kilograms a second. The question is, how is the atmosphere being lost, and where is it going? The MAVEN team carried out an ingenious analysis based on observations of the concentrations of two different isotopes of the noble gas argon, argon-36 and argon-38. Argon-38 is chemically identical to argon-36, but it's heavier because it has two additional neutrons inside its nucleus. The ratio of argon-38 to argon-36 is sensitive to the rate at which the atmosphere is being lost to space through a process known as sputtering. High-speed, electrically charged particles from the solar wind hit atoms in the upper atmosphere and literally knock them out into space. Because argon-36 is lighter than argon-38, the relative abundance of argon-36 in the upper atmosphere is enhanced In technical terminology, argon-36 has a larger scale height than argon-38. This means that argon-36 is preferentially lost to space through sputtering, and the ratio of argon-38 to argon-36 increases. Since there's no other way that argon can be removed from the atmosphere, it doesn't react with anything, and it doesn't freeze at anywhere near the temperatures seen on Mars, the argon measurements provide a very clean indication of the way the Martian atmosphere is affected by the solar wind. By using measurements from MAVEN at different altitudes during its elliptical orbit, and surface measurements of the argon isotope ratio from Curiosity, this beautifully elegant experiment enabled the team to determine that 66% of the argon in the Martian atmosphere has been lost over the planet's 4.5 billion year lifetime. Once this rate of argon loss has been determined, the rate of other atmospheric components can be calculated. The published results concluded: the evidence from MAVEN observations suggests that a large fraction of the Martian volatile inventory has been removed to space, and that loss to space has been an important process in the evolution of the Martian atmosphere through time. In particular, a large fraction of the dominant component of the Martian atmosphere, the powerful greenhouse gas carbon dioxide, has been lost to space through the interaction with the solar wind, with a smaller fraction being locked away in subsurface carbonate deposits, and an even smaller fraction stored as frozen carbon dioxide in the polar ice caps. These changes, the authors conclude, appear to be large enough to account for the change in the Martian climate inferred from the planet's geomorphology. Without declining levels of greenhouse gases in the atmosphere to keep in warmth and protect its lakes and oceans, Mars was destined to become a frozen desert world. But why has Earth not suffered the same fate? We are, after all, closer to the Sun, and bathed in a more violent solar wind. Why has our atmosphere survived the solar onslaught for several billion years, after the Martian atmosphere was stripped away?
Nicholas Copernicus was born in the Polish city of Torun in 1473 and benefited from a superb education after being enrolled at the University of Krakow at 18 by his influential uncle, the Bishop of Warmia. In 1496, intending to follow in the footsteps of his uncle, Copernicus moved to Bologna to study canon law, where he lodged with an astronomy professor, Domenico Maria de Novara, who had a reputation for questioning the classical works of the ancient Greeks, and in particular their widely accepted cosmology. The classical view of the universe was based on Aristotle's not unreasonable assertion that the Earth is at the center of all things and that everything moves around it. This feels right, because we don't perceive ourselves to be in motion, and the sun, moon, planets and stars appear to sweep across the sky around us. However, a little careful observation reveals that the situation is in fact more complicated than this. In particular, the planets perform little loops in the sky at certain times of year, reversing their track across the background stars before continuing along their paths through the constellations of the zodiac. This observational fact, which is known as retrograde motion, occurs because we are viewing the planets from a moving vantage point, the Earth, in orbit around the Sun. This is by far the simplest explanation for the evidence, although it is possible to construct a system capable of predicting the positions of the planets months or years ahead and maintain Earth's unique stationary position at the center of all things. Such an Earth-centered model was developed by Ptolemy in the 2nd century and published in his most famous work, Almagest. The details are extremely complicated and aren't worth describing in detail here because the central idea is totally wrong and we won't learn anything. The sheer contrived complexity of an Earth-centered description of planetary motions can be seen in Ptolemy's model, which shows the apparent motions of the planets against the stars as viewed from Earth. This tangled Ptolemaic system of Earth-centered circular motions, replete with the arcane terminology of epicycles, deferents, and equant, was used successfully by astrologers for thousands of years to predict where the planets would be against the constellations of the zodiac, presumably allowing them to write their horoscopes and mislead the gullible citizens of the ancient world. And if all you care about are the predictions themselves, and your philosophical prejudice and common sense feeling of stillness require the Earth to be at the centre, then everything is fine. And so it remained until Copernicus became sufficiently offended by the sheer ugliness of the Ptolemaic model to do something about it. Copernicus's precise objections to Ptolemy are not known, but sometime around 1510 he wrote an unpublished manuscript called the Commentariolus, in which he expressed his dissatisfaction with the model. I often considered whether there could perhaps be found a more reasonable arrangement of circles, from which every apparent irregularity would be derived, while everything in itself would move uniformly, as is required by the rule of perfect motion. The Commentariolus contained a list of radical and mostly correct assertions. Copernicus wrote that the moon revolves around the Earth, the planets rotate around the sun, and the distance from the Earth to the sun is an insignificant fraction of the distance to the stars. He was the first to suggest that the Earth rotates on its axis, and that this rotation is responsible for the daily motion of the sun and stars across the sky. He also understood that the retrograde motion of the planets is due to the motion of the Earth and not the planets themselves. Copernicus always intended Commentariolus to be the introduction to a much larger work, and included little, if any, detail about how he had come upon such a radical departure from classical ideas. The full justification for and description of his new cosmology took him a further 20 years, but by 1539 he had finished most of his 6-volume De Revolutionibus, although the completed books were not published until 1543. They contained the mathematical elaborations of his heliocentric model, an analysis of the precession of the equinoxes, the orbit of the moon, and a catalogue of the stars, and are rightly regarded as foundational works in the development of modern science. They were widely read in universities across Europe and admired for the accuracy of the astronomical predictions contained within. It's interesting to note, however, that the intellectual turmoil caused by our relegation from the centre of all things still coloured the view of many of the great scientific names of the age. Tycho Brahe, the greatest astronomical observer before the invention of the telescope, referred to Copernicus as a second Ptolemy, which was meant as a compliment, but didn't accept the sun-centred solar system model in its entirety, partly because he perceived it to be in contradiction with the Bible, but partly because it does seem obvious that the Earth is at rest. This is not a trivial objection to a Copernican solar system, and a truly modern understanding of precisely what at rest and moving mean requires Einstein's theories of relativity, which we'll get to later. Even Copernicus himself was clear that the sun still rested at the centre of the universe. But as the 17th century wore on, precision observations greatly improved due to the invention of the telescope and an increasingly mature application of mathematics to describe the data, and led a host of astronomers and mathematicians, including Johannes Kepler, Galileo, and ultimately Isaac Newton, towards an understanding of the workings of the solar system. This theory is good enough even today to send space probes to the outer planets with absolute precision. At first sight, it's difficult to understand why Ptolemy's contrived mess lasted so long, but there is a modern bias to this statement that is revealing. Today, a scientifically literate person assumes that there is a real, predictable universe beyond Earth that operates according to laws of nature, the same laws that objects obey here on Earth. This idea, which is correct, only emerged fully formed with the work of Isaac Newton in the 1680s, over a century after Copernicus. Ancient astronomers were interested primarily in predictions, and although the nature of physical reality was debated, the central scientific idea of universal laws of physics had simply not been discovered. Ptolemy created a model that makes predictions that agree with observation to a reasonable level of accuracy, and that was good enough for most people. There had been notable dissenting voices, of course. The history of ideas is never linear. Epicurus, writing around 300 BCE, proposed an eternal cosmos populated by an infinity of worlds, and around the same time Aristarchus proposed a sun-centred universe about which the Earth and planets orbit. There was also a strong tradition of classic orthodoxy in the Islamic world in the 10th and 11th centuries. The astronomer and mathematician Ibn al-Haytham pointed out that whilst Ptolemy's model had predictive power, the motions of the planets represent an arrangement that is impossible to exist. The end of the revolution started by Copernicus around 1510, and the beginning of modern mathematical physics, can be dated to the 5th of July 1687, when Isaac Newton published the Principia. He demonstrated that the Earth-centered Ptolemaic jumble can be replaced by a Sun-centered solar system and a law of universal gravitation, which applies to all objects in the universe and can be expressed in a single mathematical equation: F equals G times m1 m2 over r squared. The equation says that the gravitational force between two objects, a planet and a star, say, of masses m1 and m2, can be calculated by multiplying the masses together, dividing by the square of the distance r between them, and multiplying by g, which encodes the strength of the gravitational force itself. G, which is known as Newton's constant, is, as far as we know, a fundamental property of our universe. It is a single number which is the same everywhere and has remained so for all time. Henry Cavendish first measured G in a famous experiment in 1798, in which he managed, indirectly, to measure the gravitational force between lead balls of known mass using a torsion balance. This is yet another example of the central idea of modern physics. Lead balls obey the same laws of nature as stars and planets. For the record, the current best measurement of G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared, which tells you that the gravitational force between two balls of mass 1 kilogram each 1 meter apart is just less than 10,000 millionths of a Newton. Gravity is a very weak force indeed, and this is why its strength was not measured until 71 years after Newton's death. This is a quite brilliant simplification, and perhaps more importantly, the pivotal discovery of the deep relationship between mathematics and nature which underpins the success of science, described so eloquently by the philosopher and mathematician Bertrand Russell. Mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere like that of sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure, and capable of a stern perfection such as only the greatest art can show. The true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as in poetry. Nowhere is this sentiment made more clearly manifest than in Newton's law of gravitation. Given the position and velocity of the planets at a single moment, the geometry of the solar system at any time millions of years into the future can be calculated. Compare that economy. You could write all the necessary information on the back of an envelope, with Ptolemy's whirling offset epicycles. Physicists greatly prize such economy. If a large array of complex phenomena can be described by a simple law or equation, this usually implies that we are on the right track. The quest for elegance and economy in the description of nature guides theoretical physicists to this day, and will form a central part of our story as we trace the development of modern cosmology. Seen in this light, Copernicus assumes even greater historical importance. Not only did he catalyze the destruction of the Earth-centered cosmos, but he inspired Brahe, Kepler, Galileo, Newton, and many others towards the development of modern mathematical physics, which is not only remarkably successful in its description of the universe, but was also necessary for the emergence of our modern technological civilization. Take note, politicians, economists, and science policy advisors of the 21st century. A prerequisite for the creation of the intellectual edifice upon which your spreadsheets, air-conditioned offices, and mobile phones rest was the curiosity-driven quest to understand the motions of the planets and the Earth's place amongst the stars. Matching the observations of the wandering stars, the planets, of the night sky with the idea that the Earth was at the center of the solar system required extremely complex models. In the case of Venus, combining the Earth at the center with the observations meant that Venus had a circular orbit around a point midway between the Earth and the Sun, so-called epicycles, with all the other planets having similar complicated orbits around various points scattered around the solar system. Placing the Sun at the center of the solar system, with the planets arranged in their familiar order, with the Moon orbiting the Earth, gave a much simpler system.
It's a story that began before the solar system even truly existed. 5 billion years ago, a vast interstellar cloud of dust and gas, at least 65 light-years across, that's 6.1 times 10 to the power of 14 in kilometers, began to collapse and coalesce under its own enormous weight. Fragmenting into a collection of smaller, dense cores, one of these gigantic clumps formed what is known as the pre-solar nebula, the embryo from which every part of our solar system would develop. In this dense cloud of gas comprised almost entirely of hydrogen and helium, hung every atom that would go on to form the sun, the planets, and every element that would define the character of each of these worlds, including the ingredients of life, the components of you and me. What triggered this cloud beyond the tipping point and on to the next stage of its stellar evolution is lost in the eons of time, but astonishingly we have been able to pull together scraps of evidence to guide us. By studying some of the oldest meteorites ever discovered on the surface of the Earth, we've been able to get a glimpse of the time when it all began. Locked away inside these ancient meteorites are the unmistakable signatures of rare forms of iron that we believe can only have been created under a very specific set of conditions. The only place in the universe where these rare isotopes can be formed is at the heart of giant, short-lived stars at the very moment they explode. In other words, they are the product of supernovae. This clear chemical fingerprint from rocks dating back to the earliest days of the solar system, over 4.5 billion years ago, suggests that our solar system emerged among a cluster of thousands of stars in a large stellar nursery, perhaps not unlike the Orion Nebula, the star-forming region that lies closest to the Earth at 1,500 light-years away, which can even be spotted with the naked eye in the night sky. Amongst this original stellar cluster were massive stars that would have dwarfed our own, all burning hard and fast. It appears that as one of these stars reached the end of its life, its death created a supernova, and with it a shock wave that rippled through the distant origins of our solar system, causing dense regions within the pre-solar nebula to rapidly collapse. This moment provided the precise conditions for a new star to form, and thus the story of our solar system began. For the first 50 million years after the Sun was born, our corner of the universe was shrouded in darkness. The only light, the dim red glow of our embryonic star, a T Tauri-type star, struggling to shine through the very earliest years of its infancy. From that original cloud of gas, the Sun forming at its center would swallow up 99% of all the matter in the solar system, leaving just a tiny fraction that would go on to form the other planets. Yet when, after around 50 million years, the Sun's nuclear furnace ignited, its light revealed that one giant planet had already scooped up much of the remaining matter, a world 300 times more massive than the Earth is today. Jupiter, the oldest of all the planets, was there to witness the Sun's first dawn. In fact, we think Jupiter had been there from almost the very beginning of the solar system. Evidence suggests that just 1 million years after the birth of the Sun, Jupiter had already formed a core 20 times more massive than the Earth, orbiting the dark Sun and dividing the building material of the solar system into two distinct regions, each with a slightly different chemical makeup, that we would be able to observe in the signature of meteorites that fell to Earth billions of years later. Within just a few million years, this young giant was 50 times as massive as the Earth, and it would go on growing in the dark. By the time the temperature and pressure at the center of the Sun had risen so high that hydrogen began to fuse and light up the heavens, entering the main sequence phase of its life in which it continues today, Jupiter was fully grown. Under the cover of darkness before the Sun's first dawn, this planet had taken up its position of power, a formidable force that would transform the destiny of every planet that would follow. King of planets. To the Romans, Jupiter was the king of the gods, the ruler of the heavens, and a figure of power who drove forward the all-conquering Roman army with a thunderbolt in one hand and an eagle by his side. The name Jupiter itself means sky father, and it's constructed from the Latin words dies, day or sky, and pater, father. And, as is often the case with mythology, there is a truth lurking amongst the legend. In size alone, Jupiter is by far the biggest planet in the solar system. Its mass is a staggering 1,900 trillion kilograms. That's 2.5 times bigger than all of the other planets in our solar system combined. It's so big, in fact, that if you were an alien species observing our system from a distant part of the galaxy, the Sun and Jupiter might well be all you could see. With a diameter of 142,984 kilometers at the Jovian equator, the Earth would fit inside Jupiter over 1,300 times. And yet this giant of a planet is made almost entirely of gas, comprising 89% hydrogen and 10% helium. It is far less condensed than any of the rocky planets, and has a density far smaller than that of the Earth, 1.326 grams per cubic centimetre, compared with Earth's 5.513 grams per cubic centimetre. For all of its size, Jupiter also has the shortest day of any planet, completing a single rotation every 9 hours, 55 minutes and 30 seconds, as it whips around on its axis at 45,000 kilometers an hour. In the last 50 years, our knowledge of Jupiter has grown exponentially, and with it we've gained a deeper understanding of the role it has played in the shaping of the solar system. No longer just the beautiful banded world we see through our telescopes. This is a planet that we have explored up close, our eyes and ears living within the Jovian system for years at a time. The first close-up glimpse of the giant planet came with the cameras of the Pioneer 10 spacecraft in 1973. This was the first of our planetary explorers to cross the great boundary of the asteroid belt, and from an approach of just over 130,000 kilometers, it was able to take close-up images. In total, Pioneer 10 sent back over 500 precious pictures of this distant world, before flying onto the very edges of the solar system to complete its mission. Just over a year later, Pioneer 11 followed hot on the heels of its sibling craft and swept within 43,000 kilometers of Jupiter's cloud tops before heading on towards Saturn. Voyager 1 and 2 passed by Jupiter in the late 1970s, taking the first extraordinary images of not just the planet but its moons too, as part of their own grand tour of the solar system. This was an historic moment, as Fran Bagenal, scientist on the New Horizons mission, explains. We had hints, but it wasn't until Voyager went up close and personal and took amazing pictures of the moons of the planet that we really began to get a sense of just how complex the worlds around Jupiter are and what a variety there is. The Galileo spacecraft became our first explorer to actually live in the Jovian system. Entering orbit around the planet on the 7th of December 1995, Galileo spent 2 years touring Jupiter and allowed us to explore as never before. Thanks to its audacious deep dive directly into the planet, a probe that was released from the craft collected data for almost an hour as it parachuted down through 150 kilometers of Jupiter's atmosphere, before it was destroyed by the intense pressure and temperature. Galileo was also the first mission to explore the extraordinary moons of Jupiter in any detail, helping us to see for the first time that Jupiter lies at the center of an extraordinary system with more natural satellites than any other planet, holding 79 moons in its orbit at the time of writing. 12 of these satellites have been discovered since the beginning of 2017. It's almost certain that the number will rise in the coming years too, as we're able to explore the Jovian system in even greater detail. The vast majority of Jupiter's moons, 63, are not much more than fragments of rock, none bigger than 10 kilometers in diameter, and are captured asteroids that now orbit the planet rather than the Sun. But at the other end of the scale, Jupiter has 4 giant moons. Fiery Io is the most volcanically active world in the solar system, its surface littered with lakes of lava, while icy Europa is at the other extreme, with its frozen surface protecting a global ocean of water beneath. Marbled Ganymede is Jupiter's largest satellite, and the only moon we know of that has its own magnetic field, while Callisto, the outermost of Jupiter's Galilean moons, is also thought to be home to a subsurface ocean. Each moon has a unique, intriguing character, and they are all visible to us here on Earth, using nothing more than a pair of binoculars. We'll come back to these moons later in the chapter. Then, in August 2011, NASA launched its latest mission to Jupiter, Juno. After traveling for 5 years, the spacecraft reached Jupiter in July 2016 and entered into a perilous elliptical orbit that took it from 8 million to just 4,000 kilometers above the cloud tops of Jupiter's surface. Juno is a mission designed to probe for Jupiter's origin and evolution, which it does by carrying instruments to measure the planet's composition and its magnetic and gravitational fields, allowing it to build up a detailed picture of the interior. It also has the best camera we've ever pointed at Jupiter, which since 2016 has been sending back the most incredible images of the giant planet ever taken. We'll let Heidi Becker, a Jet Propulsion Laboratory physicist and the radiation monitoring investigation lead on the Juno mission, explain the detail of this incredible piece of technology. The Star Tracker is an 18-pound camera because it's passed with tungsten in order to keep the radiation out. What JunoCam's images have shown us is that Jupiter is like going to an impressionist art gallery. It's seeing Jupiter and those atmospheric features up close with the highest resolution that's ever been achieved. We're seeing the zones and belts, the jet streams of Jupiter, in more detail than ever before. For all the majesty and wonder these probes have brought us, Jupiter remains a vast, distant planet, sitting on average 588 million kilometers away from us here on Earth. It's easy to think of this world as a benign beauty, a jewel to marvel at. But what makes Jupiter the true king of the heavens is not just its beauty, but its influence over the unfolding story of the solar system. As we've explored this world ever closer, we are discovering that Jupiter's effect on the fates of entire planets is far more direct and violent than we ever imagined. Its massive gravitational field exerts control not just over its moons, but also over every asteroid, every world, and every life force in the solar system, whose destinies it still holds in its vast reach. To understand the awesome power of Jupiter, we don't need a billion-dollar spacecraft, a rocket, or even a telescope. All we need to do is to look no further than the ground beneath our feet. The surface of our planet is littered with the evidence of our distant godfathers' meddling. Written across our planet in the violent gravitational handiwork of Jupiter are, at the most recent count, 190 visible impact craters, not to mention the thousands more that have long disappeared as the active geology of the Earth's surface has continually renewed itself. One of the most famous is the Meteor Crater, also known as the Barringer Crater, in the northern Arizona desert, which measures more than 1,000 meters across and at its deepest point drops 100 meters below the crater rim. In the late 19th century, geologists believed this vast feature had been created by the San Francisco volcanic field that lies just a handful of miles to the west. But in 1903, Daniel Barringer, a mining entrepreneur and sometime hunting friend of Theodore Roosevelt, began an extensive investigation of the crater and published a set of findings suggesting that it had not been created by a volcano, but rather by a large incoming projectile from outer space. This was the first time anyone had suggested such a theory, and Barringer backed it up with a host of geological evidence, including the discovery of around 30 tons of large iron oxide fragments from the suspect meteorite. At the time, there was much skepticism that an incoming meteor could create such a massive geological feature. But ignoring the overwhelming scientific consensus, Barringer put his money and reputation firmly where his mouth was and formed the Standard Iron Company. The company was created with the sole aim of mining the crater for the 100 million tons of iron ore that Barringer believed lay in the ground, having been deposited by the incoming meteorite. Even at 1903 prices, if he'd been right, that amount of iron ore would have been worth over $1 billion. So unsurprisingly, he continued to dig down to depths of over 400 meters in his pursuit of the meteoric remains. Unfortunately for Barringer, it would take him 27 years of mining to find out what we know today. The meteorite that impacted in that Arizona desert was not only much smaller than he predicted, with current measurements suggesting it was around 300,000 tons, 300 times less than he had thought, but also, with the benefit of advanced studies in such impacts since then, most of the nickel-iron meteorite that fell was vaporized as it struck the ground at around 43,000 kilometers per hour. Barringer's money evaporated not quite as quickly as the meteorite, but by 1929 operations at the site had stopped, and most of his fortune had gone. It would be 50 years before Barringer's work would be fully and finally verified with a landmark publication in 1963. A paper by Eugene Shoemaker and his colleagues, more of him later in the chapter, analyzed the similarities between the geology of the Barringer site and the craters that had recently been created as a result of testing nuclear weapons in Nevada. Shoemaker was able to show that the shocked quartz, also known as coesite, that was identified at Barringer crater, could only have been formed at the enormously high pressures and temperatures created by a nuclear explosion, or in the case of the Arizona crater, by the extraordinary impact dynamics of a 300,000-ton meteorite crashing into the ground. We know now that the giant rock that created the crater, like most of the meteorites that strike the Earth, was once an asteroid, just one of the millions of rocks that circle the Sun between the orbits of Mars and Jupiter. Most of these have been in a stable orbit for billions of years. The rocky leftovers of the birth of the solar system, they orbit in an eternal junkyard of planetary cast-offs. But occasionally, one of these huge rocks is propelled towards the inner solar system, and more often than not, we think the nudge that causes it comes from Jupiter. Why this should happen, and how Jupiter exerts its power not just over the asteroid belt, but over all the worlds around our Sun, is a story we are only just beginning to understand. From our home here on Earth, it's hard to imagine the vast reaches of space that extend beyond our little bubble and the huge expanse of time over which events in the cosmos play out. But all the evidence suggests that around 4.5 billion years ago, Jupiter's orbit began to change, and as it did so, it triggered a period of unprecedented violence, during which the young solar system was utterly transformed. We know this because the marauding planet left a trail of destruction in its wake that we've only just begun to explore. As we've attempted to uncover the 5 billion-year history of our solar system, we've repeatedly looked to the 8 planets and the moons that orbit them to provide clues that fill in the gaps in our story. In the last 50 years, dozens of missions have crossed our thin blue line on the way to those worlds, but only once have we sent a spacecraft to explore a very different type of world, to search amongst the rubble of our solar system's earliest days and explore the handful of worlds that never quite made it. Sometimes the answers lie in the gaps. Launched on the 27th of September 2007, the Dawn space probe took off from Cape Canaveral on a mission to explore the 2 largest objects in the asteroid belt, Vesta and the dwarf planet Ceres. This $450 million project was part of NASA's low-cost Discovery program, one of a series of missions designed to be faster and cheaper to deliver. But this was no B-list mission for NASA. Equipped with the most advanced ion propulsion system ever used in outer space, Dawn would be able to reach the asteroid belt and become the first craft in the history of human exploration to enter orbit around Ceres. And yet, without a major planet in its itinerary, the attention of the world only seemed to glance towards this mission, and for the most part its extraordinary findings slipped between the gaps of public attention. The aim of the Dawn mission was simple. This would be the first spacecraft to travel to the asteroid belt, the first to orbit an object in this uncharted region of the solar system, and the first to visit a dwarf planet. All in all, this mission profile was designed to allow scientists a rare chance to travel deep into the past and glimpse the earliest moments in the origin of our solar system. The mission allowed us to explore the evolution of Vesta and Ceres, two very different objects, frozen in time for billions of years since they faltered and failed in the process of becoming fully fledged planets. To travel to the asteroid belt would be a slow but steady voyage for Dawn. After hitching a conventional ride into space on the Delta II rocket, the spaceship began firing its thrusters to orientate and propel itself away from the Earth and towards Mars. The ion thrusters on Dawn were an efficient but gentle form of propulsion for the spacecraft, taking 4 days at full throttle to accelerate the craft from 96 kilometers per hour. It's not exactly a sports car, but when it comes to efficiency, the ion propulsion system is difficult to beat. Powered by a 10-kilowatt solar array, Dawn's engines ran for almost 6 years across the 11-year lifetime of the mission, propelling the craft across space using less than 400 kilograms of its xenon fuel supply, while reaching speeds of 41,360 kilometers per hour. Its trajectory took it on a 16-month journey to Mars, where a gravitational kick sent it on its way out to the asteroid belt, and onwards towards Vesta, its first destination. Almost 500 million kilometers from the Sun, the asteroid belt lies halfway between Mars and Jupiter, the boundary line between the 4 rocky worlds that orbit closest to the Sun and the giant gas and ice planets that lie beyond. Made up of millions of pieces of rock from the dawn of the solar system, it's a graveyard of failed planets, remnants from the heyday of planetary construction. We often imagine the asteroid belt to be a dense, unnavigable mass of tumbling rock, but in reality it's something quite different. The total mass of all those rocks is estimated to be 3 times 10 to the power of 21 kilograms, which, although an enormous-sounding number, is just 4% of the mass of our Moon, with a third of that mass found just in the largest object, Ceres. The rest of this cosmic junkyard is made up of objects covering a vast range of different sizes. On one end of the scale, we think there are at least a couple of hundred asteroids larger than 100 kilometers in size. Then come a million or so stretching to at least 1 kilometer or more, and a countless spread of smaller objects number in the millions and billions, depending on how small you want to go. All of this sounds like it should make for a crowded environment full of collisions, the perfect location to form the basis of a computer game or disaster movie. But even with that many objects, the space they occupy is so unimaginably vast, spread out across 13 trillion cubic miles of space, making the average distance between any 2 large asteroids approximately 2 million miles, or 8 times the distance from the Earth to the Moon. These distances are so large that when we send spacecraft to the outer solar system, the chances of hitting anything are so small that the engineers don't need to make any course corrections to pass through. In fact, if you were standing on an asteroid, you'd be lucky to see another one, and if you did, it would appear as little more than a tiny point of light in the darkness. As it travelled through this vast emptiness in the early summer of 2011, the Dawn spacecraft slowly began to bring its first target into view. From a distance of over 1.2 million kilometers, Dawn took its first photograph of Vesta against the backdrop of 1,000 stars. Over the next 2 months, Dawn homed in on Vesta, chasing it across the vast reaches of space to arrive at this, the second largest rock in the belt. Entering its orbit on the 16th of July 2011, Dawn became the first spacecraft to enter within the gravitational hold of an object in the asteroid belt. And for the next 14 months, it would explore this extraordinary ancient object, providing a glimpse of our solar system in the very earliest days of its life. When 4 Vesta, to give it its full name, was first discovered by the German astronomer Heinrich Olbers in 1807, it was the 4th asteroid to be discovered after Ceres, Pallas, and Juno, hence the 4 in its formal designation. Olbers was convinced he had found the remains of a lost planet, destroyed in some long-ago collision. Even so, just like the other 3 objects, at first Vesta was given full planetary status, bringing the number of classified planets in the solar system at that time to 11. It wasn't until 1845, nearly 40 years later, that a flood of further discoveries began that quickly increased the number of objects in this region to a point where it was clear they couldn't be classified as planets. And so in the 1850s, 15 planets became 8, and the classification of these objects as a different class of minor planet, asteroids, had begun. 160 years later, as Dawn began its year-long residency in the vicinity of Vesta, it soon became apparent that Olbers' suggestion that this was a fragment of a long-lost planet was not so far off. Vesta is a spheroid-shaped rock, 530 kilometers in diameter and pockmarked with impact craters. The most striking example of these is the crater Rhea Silvia, which at 500 kilometers wide and 20 kilometers deep is one of the largest impact craters in the solar system. At its center is a mountain that rises into the blackness 22 kilometers from the crater floor, making it the second tallest peak in the solar system after Mars's Olympus Mons. What's particularly extraordinary about this crater is that we've long suspected that a particular class of meteorite found on Earth, known as HED meteorites, actually come from material that was blown off the surface of Vesta when this impact occurred around 1 billion years or so ago. Using Dawn's instrumentation, we were able to directly measure the geology of rocks in Rhea Silvia, and when compared with the samples on Earth, we were able to conclude that they are of the same origin. In one of the most beautiful examples of geological analysis in the history of the subject, we now know that we can hold a piece of this faraway asteroid in our hands and directly analyze the secrets hidden within it. When taken all together, the HED meteorites and the findings from the Dawn spacecraft have enabled us to paint a detailed picture not just of Vesta today, but also of its history. Dawn has revealed to us that Vesta has a metal-rich core, just like all of the terrestrial planets, including Mercury, Mars, Venus, and Earth. And analysis of its surface geology has enabled us to date the formation of the asteroid to a couple of million years after the first solid objects began to take shape in the solar system. These are just two of the clues that point us to an extraordinary conclusion. Vesta is perhaps the last remaining example of a protoplanet, a half-formed world from the very earliest days of the solar system. Frozen in time, this is a stage that every world we know of passed through, including the Earth. Vesta was on the way to becoming a planet almost 4.5 billion years ago, but something happened to stop its progress. While other worlds went on to flourish, and other protoplanets disintegrated in the violent collisions of the early solar system, Vesta somehow seemed to survive, a fossil of planetary formation for us to not only look at, but through a quirk of fate, actually hold. But this was not the end of Dawn's dive into our deep history. Departing Vesta after 14 months of study, Dawn fired its ion drive, leaving the orbit and heading off for its second planetoid rendezvous, at the largest of all the asteroids, Ceres. Ceres' secrets. Dawn arrived at the dwarf planet Ceres in early March 2015, and from the very first moments of its observations, it sent back some astonishing images. Very little was known about Ceres before our spaceship arrived, but it soon became clear that this was a rock with far more of a story to tell than we could ever have imagined. A story that would help reveal a new perspective on the deep history of our solar system and the enormous influence Jupiter has exerted over it. The Italian astronomer Giuseppe Piazzi discovered Ceres on the 1st of January 1801, and at first he reported his findings as the discovery of a new comet in the region of space between Mars and Jupiter. But it seems from the start that all of his instincts told him this was something else. In announcing his observations in a letter to two fellow astronomers, he noted that since its movement is so slow and rather uniform, it has occurred to me several times that it might be something better than a comet. Piazzi and his colleagues speculated that rather than a comet, they might have found something even more spectacular, a new planet. But after just 41 days of observation, Piazzi fell ill, the path of the newly discovered object strayed into the direct glare of the sun, and in a twist of high astronomical drama, the newly found planet Ceres was lost. With just a tiny number of observations across a small piece of sky, calculating Ceres's orbit was deemed impossible using the mathematics of the time, and many contemporary great mathematical minds predicted it might never be found again. It would take the work of a young German mathematician Friedrich Gauss to solve the problem. Attracted to the difficulty and elegance of using mathematics to compute the orbit from just a few coordinates, Gauss pioneered a novel mathematical method that allowed him to calculate the path of Ceres using just 3 of Piazzi's original observations. On the very last day of 1801, 2 astronomers using Gauss's methods searched the region of the sky to which the calculations guided them, and to everyone's delight and relief, recovered Ceres from the darkness. Gauss became a mathematical superstar, and Ceres, firmly back in our sights, was stamped with the classification of a planet. For the next 50 years, Ceres and its companions, Vesta, Pallas and Juno, remained listed as planets until, as we have seen, the discovery of a raft of other objects in this region of space gave rise to our identification of the asteroid belt, and for Ceres it was downhill from there on, until in 2006 it was classified as a dwarf planet. For the next 160 years, little was known about this tiny planet orbiting the Sun at a distance of 413 million kilometers. We knew that it was the biggest object in the asteroid belt, and the only object amongst the millions of asteroids that was large enough to have been rounded by its own gravity. We could also make a good approximation of its size, at around 1,000 kilometers in diameter, and composition, rock and ice, what else? But when it came to surface features, even the powerful eye of the Hubble Space Telescope could make out only the vaguest of features, intriguingly strewn across its surface. It would take Dawn's arrival for us to truly understand the complexity of this world and its history. Even in the early approach phase of the mission, Dawn was able to capture a quality of imagery that at once gave a new perspective on the long-hidden surface. It was no surprise to find it heavily cratered, but while speeding towards Ceres, Dawn beamed back a series of mysterious images, revealing a number of bright spots on the surface of what we had thought would be a dull, dead and frozen world, not what you would expect on a planet that was assumed to be entirely geologically inactive. The brightest of all of these highly reflective areas was imaged near a massive crater known as a crater. At 92 kilometers wide and 2 kilometers deep, it's one of the biggest on the surface of Ceres. Spot 5, as it became known, is in the center of the crater and became the focus of intense investigation as Dawn began its 3.5-year residency in orbit around Ceres. The crater is thought to have formed from a large-scale impact around 80 million years ago, and so the presence of what appeared to be geological active material on the surface was particularly surprising, and at first left the mission scientists perplexed. Not only that, but a haze was also seen to periodically appear above Spot 5, suggesting something was going on beneath the surface. After detailed analysis using Dawn's full range of imaging and spectroscopic capabilities, we now believe that Spot 5 is the result of a geological hotspot, the brightness created by the highest concentration of carbonate minerals ever found outside the Earth, in a dome structure right in the center of the crater. Why does this matter? Well, we know that this type of salt can only be formed in the presence of liquid water, and it's almost certain that an impacting asteroid could not have delivered such material to the surface of Ceres, so the upwelling in which it's found suggests that it comes from deep within this world. It now seems that Spot 5 is the remains of an ice volcano, one that is perhaps still partially active, and thus able to create the haze we have observed. The 2 brightly colored patches inside it are thought to be the salty residue left by this ancient formation, deposits of sodium carbonate from an erupting ice volcano that may have first been triggered by the impact that created the crater. However, the dome-like shape upon which the deposits sit is almost certainly evidence of geological activity below the surface, suggesting that hydrothermal activity was involved in bringing the salts to the surface. And Spot 5 is far from isolated. We've now seen areas like the ones in Akator all over the surface of Ceres, and this begins to paint a tantalizing picture of Ceres' past, a past where heat from within the planet created a subsurface ocean, or at least localized pockets of water that surged upwards in the form of great ice volcanoes, bringing with them on the asteroid the carbonate salts that we see sparkling today. As dawn delved deeper beneath the surface, the surprises kept coming thick and fast. Dawn was able to accurately measure the overall density of Ceres and found it to be 2.16 grams per cubic centimetre, which is less than you'd expect for a rocky body. Ceres is about 2/3 the density of our Moon, which suggests that as well as rock, the asteroid must also hold significant amounts of water ice. This had been suspected long before Dawn arrived, but with our eyes and ears now at work, as Dawn circled Ceres, it was able to take precise measurements and so uncover anomalies in its orbit that revealed something remarkable about this lump of rock and ice. By carefully mapping the shape and gravitational field, we found that the rock and ice weren't evenly distributed. It appears that Ceres' interior is nothing like that of other asteroids in the belt. Instead, it appears to have a rocky core surrounded by an ice-rich crust. This is not the jumbled structure of an asteroid. The differentiation into layers that was discovered by Dawn is something we only see in planets. It seems that around 4.5 billion years ago, Ceres had taken its first steps to becoming a fully fledged world, and then something went catastrophically wrong. So we now think that 4.57 billion years ago, a young rocky planet began to form in the region we call the asteroid belt. In its infancy, this protoplanet was a water world, warmed from within by the heat left over from the violence of its birth. Even in this frozen region of space, orbiting 413 million kilometers away from the weak young Sun, a deep saltwater ocean encircled the young Ceres, protected from the freezing temperatures of space beneath a thin layer of ice. Across this ancient embryonic world, ice volcanoes broke through, transforming and renewing the surface as it was bombarded by the bodies that swarmed around it. Today we see just the lifeless remains of this geologically active world in the distinct mountainous landscape and sparkling salts that clothe it. But the subsurface ocean is long gone, locked away as a thick layer of ice between the surface and the core. This is a nascent planet that has been in deep stasis for billions of years. Frozen in time, it is a precious piece of history, an artifact that allows us to glimpse our origins and understand just how precarious a time this was for every planet, including our own. We now think that before Ceres could fulfill her potential, a great disturbance sent shock waves through what would eventually become the asteroid belt and cut its young life short. The vast amounts of rock and ice that made this part of the young solar system such a rich breeding ground for the birth of planets was wiped clean of almost all of its building material, leaving just a fraction of the material needed to build a planet, and nothing from which Ceres could grow. Computer simulations suggest that originally the asteroid belt contained enough material to build a planet the size of Earth, and perhaps that was once Ceres' destiny. Perhaps it was even destined to become a subterranean water world capable of supporting and nurturing life. But before any carbon chemistry could spark into seeds of life, Ceres' fate was sealed, triggered by the wanderings of a giant that lay beyond in the darkness. We now suspect that at this early time in the life of the solar system, as Jupiter circled the young Sun, something caused the giant planet to change course and spiral inwards towards the Sun, ploughing right through the asteroid belt. The resulting gravitational chaos scattered the contents of the asteroid belt far and wide. Embryonic planets were knocked out from their orbits. The building material of these planetesimals was thrown out and in towards the Sun. Jupiter's charge displaced 99.9% of the material in this region of space, leaving Ceres half-formed, half-built, but with nothing more from which to grow. In this part of the solar system at least, the planetary construction business was shut down for good.
Let us now return to Frank Drake's equation and use it as intended as a framework to address in a systematic manner the question of our solitude. Recall that the equation consists of a series of terms which, when multiplied together, give an estimate of the number of currently contactable civilizations in the Milky Way galaxy. At the 1961 Green Bank meeting, only the first term, the rate of star formation in the Milky Way, was known with any precision. Over half a century later, we can do much better. The next term in the equation is the fraction of stars in the Milky Way that have planets orbiting around them, most definitely a prerequisite for an intelligent civilization to emerge. It's true that the civilization may not have remained confined to its home world, and we will discuss this possibility later on, but it must be true that for life to emerge and evolve to the point where it can build spacecraft, a planet of some sort is required. This space we declare to be infinite. In it are an infinity of worlds of the same kind as our own. Giordano Bruno, 1584. The existence of alien worlds has been speculated about for many centuries. Ever since Copernicus began the process of demoting our solar system from its preferred place in the cosmos, it has been natural to assume that at least some of the stars in the sky must have planetary systems. Yet despite this seemingly common-sense conclusion, reached by virtually every right-thinking astronomer from Giordano Bruno onwards, the existence of other planets remained nothing more than an educated guess well into my lifetime. The vast distances between the stars and the limitations of technology locked us inside our own solar system with no way of seeing beyond. Throughout the 19th century, a number of astronomers claimed to have detected distant planets, but all these observations proved to be flawed. Today, the picture couldn't be more different. The night sky is known to be awash with worlds. One of the more enticing of the known solar systems is located around a slightly smaller, cooler version of our Sun called Kepler-62. Around 1,200 light-years from Earth in the constellation of Lyra, the system has been widely studied because it has at least 5 planets. 2 of them, Kepler-62e and Kepler-62f, are particularly interesting because they are Earth-like in both size and distance from the star. Bathed in Kepler-62 shine, these worlds may, if they have the right atmospheric conditions, support oceans of liquid water on their surfaces. We will discuss the significance of this in the context of life later on. The discovery of extrasolar planets has been possible due to the rapid development of precision astronomical instruments, both space-based and terrestrial, that allow us to see beyond the bright glare of stars to the worlds that lie in the shadows. Imagine looking at our solar system from the nearest star system to Earth, Alpha Centauri. The system is 4.37 light-years away and consists of 2 sun-like stars, one slightly more massive than the other, orbiting each other with a period of approximately 80 years. The red dwarf Proxima Centauri is probably a distant, gravitationally bound component of the system, making it a loosely bound triple star. Looking back towards Earth from 40 trillion kilometers with the naked eye, our Sun would look like any other solitary star. Detecting exoplanets is no easy task because planets are vanishingly small and faint, masked by the brightness of their parent stars, and directly imaging them remains a major technical challenge. To step out of the glare has required the development of indirect methods of detection based on surprisingly sensitive technologies. On the 21st of April 1992, the first conclusive detection of an exoplanet was made by radio astronomers Alexander Vorschan and Dale Frail, working at the Arecibo Observatory in Puerto Rico. They were hunting for planets around a pulsar known as PSR 1257+12, located 1,000 light-years from Earth, using a delicate method of indirect observation known as pulsar timing. Pulsars are spinning neutron stars, some of the most exotic objects in the universe. PSR 1257+12 is 50% more massive than our Sun, but has a radius of just over 10 kilometers. It is, in effect, a giant atomic nucleus, spinning on its axis every 0.006219 seconds. That's 9,650 RPM. As you may gather from this rather precise statement, it's possible to measure the spin rates of pulsars with great precision by timing the interval between pulses of radio waves emitted from the stars like a lighthouse. Volschan and Frail reasoned that if a large enough planet was orbiting a pulsar, the gravitational tug should shift the arrival times of the radio pulses by enough to be detectable. And sure enough, they found 2 planets orbiting PSR 1257 plus 12 and measured their masses and orbits. Planet A has a mass of 0.020 times the mass of Earth and orbits the star once every 25.262 days. Planet B is 4.3 times the mass of Earth and orbits once every 66.5419 days. Subsequently, a third planet has been discovered with a mass of 3.9 times that of Earth and orbiting every 98.2114 days. Pulsar astronomy is indeed a precision science. This was an historic observation, but of limited direct interest to SETI, since there is absolutely no chance that life could survive the hostile environment around such a violent astronomical object. It was, however, an existence proof, the first discovery of planets beyond our solar system, and a surprising one at that. To search for Earth-like planets around Sun-like stars required the development of different but equally beautiful methods of observation. The first of these to be deployed was the radial velocity method. A star doesn't sit still at the center of a solar system with planets orbiting around it. Rather, the star and planets orbit around their common center of mass. The center of mass of a solar system with a single star will always be inside the star itself, because it carries virtually all of the mass, but the star will still wobble around the center of mass of the system as seen from Earth. This planetary-induced wobble is small but measurable. In our solar system, Jupiter causes our Sun to wobble backwards and forwards with a velocity change of approximately 12.4 meters per second across a period of 12 years. The Earth's effect is minute in comparison, inducing a velocity change of just 0.1 meters per second over a period of a year. In the 1950s, future Green Bank pioneer Otto Struve suggested that such a planetary-induced wobble could be detected using the Doppler effect. When a star moves towards the Earth, its light is shifted towards the blue part of the spectrum, and when it moves away from the Earth, its light is shifted towards the red part of the spectrum. By making measurements of the specific frequencies, i.e. colors of light absorbed by chemical elements in the star's atmosphere, and measuring how much these are shifted relative to the known frequencies as measured here on Earth, the motion of the star backwards and forwards can be determined over a period of time, and this can be used to calculate the orbital period of the planet and to estimate its mass. If there's more than one planet, the motion of the star will be more complicated, but since the orbital periods of the planets are regular, the contributions of the different planets to the star's wobble can be figured out. Struve was one of the first respected scientists to publicly state his belief in extraterrestrial life. In the 1950s, however, the spectrographs used to measure red and blue shift were only able to detect velocity changes of a few thousand meters per second, and at the Green Bank meeting, he could only speculate that his technique would one day confirm his prejudice that planetary systems are common. Struve didn't live long enough to see his method applied, dying just 2 years after Green Bank, long before technology caught up with his ambition. It took until 1995 for 2 Swiss astronomers, Michel Mayor and Didier Queloz, to detect a planetary-induced Doppler shift using the Observatoire de Haute-Provence in France. The team discovered a planet orbiting the Sun-like star 51 Pegasi, located 50.9 light-years from Earth. This planet is named 51 Pegasi b, but its nickname is Bellerophon, after the mythological Greek hero who rode Pegasus, the winged stallion. Since its historic discovery, Bellerophon has been observed and examined in quite some detail, and it is no second Earth. It is a deeply hostile world, orbiting its parent star every 4 Earth days, on a trajectory that takes it far closer than Mercury approaches our own Sun. Unlike Mercury, Bellerophon is a gas giant planet, with a mass 150 times that of the Earth, and a surface temperature approaching 1,000 degrees Celsius. Although only half the mass of Jupiter, It may have a greater radius because the high surface temperature causes it to swell. Such exoplanets are known as hot Jupiters, big enough and close enough to cause a significant wobble in their parent stars, which is why these types of worlds were discovered first by the early planet hunters. The first evidence of a potential Earth-like planet arrived in 2007 when Stéphane Audrey and his team at the European Southern Observatory in Chile announced the discovery of a planet around the red dwarf star Gliese 581, just over 20 light-years from Earth. This was the second planet to be discovered in this system, but Gliese 581c made headline news around the world because of its apparent Earth-like qualities. This planet is a rocky world, about 5 times as massive as Earth, and possibly the right distance away from its parent star to support liquid water on the surface, the stuff out of which science fiction dreams are made. Further research has cast doubt on the idea that Gliese 581b might have the necessary conditions to support life, but in March 2009, the second Earth hunters got their own dedicated scientific instrument, and with it a cascade of new data became available. The Kepler Space Telescope has transformed our knowledge of the distribution of planets in the Milky Way. Kepler is not a general-purpose instrument with multiple detectors and myriad ambitions. The telescope was designed for one purpose: to look for Earth-like planets. Free of the distorting effects of the Earth's atmosphere, Kepler carries a high-precision photometer, an instrument that has measured the light intensity from over 100,000 stars considered stable enough to support life on planets around them. Kepler searches for planets using a technique known as the transit method. If a planet passes across the face of a star as seen from Earth, the observed brightness of the star will drop by the tiniest of margins. Kepler's photometer is so sensitive it can measure changes in brightness. To use precise astronomical language, we should say changes in the apparent magnitude of less than 0.01%. Observing repeated dips in brightness allows the orbital period of the planet to be measured, and the details of the changes in the brightness, combined with knowledge of the orbit, allows the size and mass of the planetary candidate to be estimated. The transit method has been extremely successful in the hunt for exoplanets, but the technique is not entirely reliable, often throwing up false positives. Once a promising candidate is found, the location is passed to ground-based telescopes for further analysis, and if confirmed, the planets are classified as discoveries. Kepler has used the transit method of planet hunting on a quite extraordinary scale, since it became fully operational in May 2009. As I write in July 2014, NASA's Exoplanet Archive lists 1,737 confirmed planets, over 50% of which have been discovered using the Kepler data. This number is all the more staggering because Kepler is only capable of detecting a very small number of the planetary systems in our galaxy. Kepler views around 0.3% of the sky in the constellations of Cygnus, Lyra and Draco, and even in this small patch, the telescope can only detect planets that pass directly in between their parent star and Earth. If the plane of the planetary orbits is orientated at the wrong angle, which is more likely than not, Kepler will not see any planets. Furthermore, Kepler only observed for 4 years, and because it has to see more than one transit to measure an orbit, it is blind to planets that orbit with periods greater than 4 years, which is the case for all the outer planets in our solar system. And finally, Kepler only sees stars out to a distance of approximately 3,000 light-years, whilst our galaxy has a diameter of 100,000 light-years. Kepler's data set, then, contains only a tiny fraction of the planetary systems out there. All of these losses can be corrected for in a statistical sense, and when the numbers are crunched, we have a reliable observation-based number to put into the Drake equation. The fraction of stars that have planetary systems is close to 100%. On average, there is at least one planet per star in the Milky Way galaxy, and we can insert the second term with confidence. Fp equals 1. The extraordinary Kepler mission was expected to last until 2016, but technical malfunctions may mean the telescope has now finished its planet hunting activity. Even so, the huge volume of data is still being worked through, and indications suggest it may have captured evidence for up to 3,000 more planets circling distant stars. This is encouraging for SETI enthusiasts, but in the hunt for civilizations, it's not the number of planets out there that really matters. Rather, it's how many of those planets are capable of supporting life. This is the next term in the Drake equation, the average number of planets per star that has planets that can support life, NE. This is sometimes referred to as the Goldilocks question. How many of those billions of planets are not too hot and not too cold, but just right to allow life to exist on their surface?
How do we know such a dramatic turn in the solar system's history took place? The greatest evidence has come not from our own system, but from the study of other star systems and their planets, a field of science that has exploded in the last 30 years. Until the 20th century, the only evidence of how planetary systems formed and functioned came from one single source, Earth's solar system. Our own backyard was the one place that we had the technology to study, and that meant our view of how a planetary structure worked was deeply skewed towards the seemingly simple structure of a star at the center, 4 small rocky planets orbiting it, then a ring of millions of rocky pieces, remnants from its formation, followed by a series of 4 more planets, the gas giants. It has a pleasing, regular structure about it, all the rocky planets sitting close to the star and the gas giants orbiting further out. We supposed this must be the natural order of things, the way that solar systems have to form. But that all changed when the technology arrived to allow us to detect planets around distant stars. It soon became clear that our solar system is not typical at all. It may, in fact, be very odd indeed. In most of the planetary systems we've observed, the setup is remarkably different to our own. As we have extended our gaze and explored the structure around other stars with the help of exoplanet hunting technology like the extraordinary Kepler telescope, we've begun to see that one of the most commonplace categories of planet is completely missing from our own. Inward of Mercury, our solar system is essentially an empty void. But look at the equivalent region around most stars we have studied, and we often find it packed with a completely different class of planet, super-Earths. These worlds are between 2 and 8 times the mass of the Earth, with thick hydrogen-rich atmospheres. They sit incredibly close in to their stars, orbiting at a rate that makes the head spin. The first discovery of a super-Earth around a main sequence star like our own was made back in 2005 by a team led by Eugenio Riviera, using data from the Keck Observatory in Hawaii. Gliese 876d is an exoplanet almost 7 times the size of the Earth, which is orbiting just 3 million kilometers away from its red dwarf star, Gliese 876. Thought to be a rocky planet with surface temperatures estimated to approach 341 degrees Celsius, with an orbital period, year, of just under 2 days, this is a world completely inhospitable to life. To understand why this rocky planet is found so close in to the Sun, we need to understand the rest of the planetary system. And in the case of Gliese 876, that means looking at the 3 other planets circling further out from the star. The first of these planets to be discovered, and one of the earliest ever observations of an exoplanet, is 876b. Discovered in 1998 by the legendary planet hunter Jeff Marcy, we believe this world is a gas giant at least twice the size of Jupiter, but orbiting much closer to its parent star. In fact, at just 0.2 AU, 30 million kilometers, this massive planet is orbiting much closer in than Mercury orbits the Sun. At that distance, 876b zooms around on its orbit once every 61 days, compared with Jupiter's stately 12-year journey around the Sun. Either side of this giant planet are 2 other worlds, 876c, a gas giant 3/4 the size of Jupiter, and 876e, a planet we think is about the same size as Uranus. All 4 of these worlds orbit within a distance less than the orbit of Mercury. It's as if the whole planetary system has been squashed, packed in tightly around the star, and this configuration is far from rare. As we've explored more and more planetary systems, we've discovered this combination of super-Earths and close-orbiting gas giants is the nearest to a normal layout we observe. What underlies this is the fact that planetary systems are not the static and stable systems we had always assumed them to be. Far from the heavens being full of planets following eternal clockwork rhythms, most systems, including our own, are chaotic, dynamic, and turbulent. The reason for this is that, particularly early on in the infancy of a new system, planets frequently migrate, forming in one part of the system before wandering off into different zones. There are a number of different mechanisms behind these wanderings, but perhaps the most formative on the evolution of a planetary system is the Type 2 migration that occurs to gas giants early on in their lives. A gas giant planet like Gliese 876c would almost certainly have begun its life far further out than it is today, in a region more akin to where we see Jupiter or Saturn in our own solar system. At the very earliest stages of its existence, as this newly formed planet orbited within the cloud of gas and dust of its formation, the planet began to clear a path in its wake, and in doing so triggered a process that would transform its orbit. A shift in its gravitational interactions with the gas-rich disk would have slightly reduced its angular momentum and sent the planet on a different course, spiraling inwards towards the star at the center of the system. This seems to be a common path trodden by many gas giants around distant stars, and is the reason we find a preponderance of so-called hot Jupiters, massive gas giants sitting so close to a star that they orbit it in less than 10 days. The effects of these migrations have an impact far greater than just this, though. In ploughing inwards, a migrating gas giant like Gliese 876c ends up clearing vast areas of space, halting any planetary formation, and instead pushing material inwards towards the star, creating the perfect scenario for super-Earths like 876d to form. This cosmic pinball is the reason why so many of the planetary systems we've been able to explore follow the pattern of hot-ish Jupiter and super-Earths. But why not ours? What was different about the history of our solar system that led to the more expansive layout we see today? Scientists suspect the answer lies with our own gas giant, Jupiter, and the journey it took across the young solar system. The story of Jupiter begins not in the far reaches of the solar system, 778 million kilometers from the Sun, where it orbits today, but much closer in. We now think that almost 5 billion years ago, Jupiter formed around 520 million kilometers, 3.5 AU, from the Sun. At this time, the young giant was still surrounded by the disk of gas and dust from which it had arisen. But Jupiter began to slowly but surely clear its path through the cloud and debris. Over a relatively short period of time of just a few million years, the path through its orbit became completely clear, and just like the huge gas giants we've observed around alien stars like Gliese 876, this caused Jupiter to start spiraling inwards towards the Sun. This process was driven by the gravitational interaction between Jupiter and the cloud of gas, which, as it fell into the Sun itself, effectively dragged the planet with it. This was no subtle shift in Jupiter's orbit. While it spiraled inwards, it would keep falling closer and closer to the Sun, passing through the region of asteroid belt and robbing planetary hopefuls like Ceres and Vesta of the material they needed to complete the journey to planethood. But this was just the start of Jupiter's reign of terror. Further and further the young Jupiter fell, until it reached the vicinity of where Mars orbits today, just 225 million kilometers or so from the Sun. This was no quiet visitor to our local neighborhood. A planet of this size can wreak havoc just by its proximity, and Jupiter's arrival in the inner solar system did just that, transforming the destiny of many of the emerging new worlds, including our own. Lee Fletcher, from Jupiter Icy Moons Explorer mission, explains this action as a tug-of-war. Between the orbits of Mars and Jupiter, we have a large accumulation of objects, rocky objects mostly, known as the asteroid belt. They're not able to form and agglomerate into a complete planet, because of the constant tug-of-war between the gravitational forces of the Sun and of Jupiter. So what we see today is a large disk of objects that could be the remnants left over from the formation of our solar system. To understand just how powerful a presence Jupiter must have been as it marauded around the inner solar system, we need to look no further than the worlds it has in its iron grip today. Jupiter has, at the time of writing, 79 known moons held in its orbit by the powerful gravitational field that is generated by the planet's enormous mass, a powerful force field that reaches out from the planet deep into the solar system. It's what has made Jupiter so destructive in the past, and through our exploration of the Jovian system, we have also witnessed its awesome power today. Nowhere is this power more dramatically revealed than on Io, the closest of all the moons to Jupiter. Io orbits just 350,000 kilometers from the cloud tops of its mother planet, a distance that makes it a gravitationally tortured world. A volcanic vision of hell, this is the most geologically active object in the solar system, with over 400 active volcanoes, from which lava flows stretch hundreds of kilometers across the moon's surface, and vast clouds of pyroclastic material blow hundreds of kilometers up into space, creating distinctive umbrella-shaped plumes above its surface. The surface of Io is perhaps the closest that our solar system has to offer of a vision of hell, and all of this activity is created not by ancient internal heat as we see on our planet Earth, but by the power and the influence of Jupiter's gravitational pull. Here on Earth, the volcanism that we see across our planet is driven by a combination of the heat that remains from our planet's violent formation and that which is released from the decay of radioactive elements locked away in the planet's interior. This heat, combined with the high pressures below the surface, creates the molten rock that pools within the mantle layer of the Earth, and then in certain places this magma finds a route to the surface, creating a volcano. On Io, the volcanism is nothing like this. Instead, it's being generated by a completely different mechanism, a process called tidal heating, that is driven in large part by its proximity to Jupiter and the gravitational tug-of-war between other nearby moons. Io is caught between the vast mass of Jupiter on one side and the three other Galilean moons, Europa, Ganymede, and Callisto, on the other, a dynamic that pulls in different directions to violent effect. It's a dynamic that we see in part on our planet every day, as the force of gravity flexes its muscles in the interaction between the Earth and the Moon, creating the twice-daily ebb and flow of our tides. On Earth, the gravitational tug of the Moon creates a tidal force that moves vast volumes of water around the planet, with the biggest difference between low and high tide creating a shift of a maximum of 12 meters in the height of water. The same principle also applies on the surface of the Moon, where the gravitational pull of the Earth creates tides not of water, but of rock. Moon tides are small changes in the height of rocks on the lunar surface caused by the pull of the Earth's gravity. In the case of the Earth-Moon system, these rock tides are measured in just a few centimeters, but Io tells a very different story. Io is roughly the same distance from Jupiter as our Moon is from Earth, and both moons are of equal size. But because Jupiter is so much more massive, the tidal forces it generates are much greater, with the gravitational pull of Jupiter moving the bulge of rock tides up to 100 meters between low and high tide. That's 5 times the height of any tide here on Earth, lifting the levels of solid rock up and down. In fact, Io contains the least amount of water of any known object in the solar system. But this is not the end of Io's torture. Its relationship with the other large moons, particularly the next moon out, Europa, also adds to the destructive forces that are pulling the very substance of Io apart. Io whips around Jupiter much quicker than our Moon goes around the Earth, once again due to the mass of Jupiter, completing an orbit once every 42 hours. If left alone, Io would complete this orbit in a near-perfect circle around the giant planet. But Io is far from alone, and with Europa circling Jupiter precisely once every 2 orbits of Io, it means that in every second orbit, Europa and Io line up, and that rhythmic orbit has consequences. This is what's known as an orbital resonance, and the result is that it gives Io an additional gravitational kick that moves the Moon's orbit out of a circle and into an ellipse. Ganymede is also in a resonant orbit with Io in a 1:4 orbital period ratio, and the outcome of this is that as Io orbits, the gravitational forces are constantly shifting and changing, and that stretches and squashes the Moon, creating vast amounts of friction that causes its interior to heat up. It's a process called tidal heating, and it's this generation of heat that produces Io's volcanoes, raising the temperature in its interior to over 1,200 degrees Celsius, and creating the violent world of lava lakes and volcanic plumes that we've witnessed through the eyes of Galileo and Voyager. The pull of the two moons on Io also stops it gradually falling inwards to Jupiter and being completely ripped apart. Io is an extraordinary example of the power of Jupiter, and a demonstration of how this planet can shape and change the destiny of worlds. Because of its huge mass and the intense gravitational force this produces, any planet or moon that gets too close to it is under threat. While Earth is at a relatively safe distance today, 4.5 billion years ago, as Jupiter moved into the inner solar system, it began to exert its power right in the spot where Mars and our own world were beginning to form. 4.5 billion years ago, the region of the solar system we call home was densely packed with gas and rock, a planetary nursery full of embryonic worlds, each with a different destiny in store. But this fertile space was about to be thrown into chaos by the solar system's most unwelcome of visitors. As Jupiter was pulled from its distant orbit and continued its inwards descent, it paused in this planetary breeding ground. The consequences of this action would be significant and far-reaching. Detailed simulations of the impact this wandering Jupiter would have made suggest that the fate of any super-Earths caught in mid-formation would have been thrown into chaos. The models suggest that Jupiter's inward journey would have driven thousands upon thousands of planetesimals, many over 100 kilometers wide, spiraling into the inner solar system. This planetary breeding ground was turned into a battleground, as Jupiter's presence threw the orbits of any newly forming super-Earths into the overlapping paths of thousands of massive blocks of rock and ice. The result was carnage, a cascade of collisions that blew apart planets and left a trail of fragmentary worlds in its wake, a chain reaction that would culminate in the formation of a spiraling swirl of gas, dust, and rock that would have swept any surviving super-Earths towards the Sun and ultimately to their destruction. In what was just a fleeting moment in the history of our solar system, its destiny changed forever. Our planet would not fit the norm of super-Earths and the tightly packed gas giants that we see across the Milky Way. Instead, we think the inner solar system would have been swept clear of up to 90% of the rocky material thrown in by Jupiter. With just crumbs remaining, 4 small terrestrial planets began to form from the rubble. With Jupiter marauding in its orbit, much of the material that could have gone on to form Mars was lost, leaving the planet with enough scraps to make a planet half its potential size, and transforming it from a possible habitat for life to a world that would freeze and die in its adolescence. Just that little bit further in, Earth found itself forming in a slightly more substantial ring of gas and dust that would make it the largest of all the terrestrial planets. A lucky escape for our future home, because had Jupiter continued on its inward path, Earth might never have formed at all. But just as it looked like it would sweep everything away, Jupiter stopped in its tracks. On its inward journey, Jupiter had transformed the inner solar system, sweeping away the formative giant planets and leaving just enough material for Mars, Earth, Venus, and Mercury to form. But the stage was now set for another player to enter the story and shift the destiny of both our world and the solar system once again. Waiting in the shadows of the outer solar system, another massive planet was lurking that we now think pulled Jupiter back from the brink. Saturn, a gas giant not as big as Jupiter but enormous nonetheless, began its own slow drift inwards towards the Sun. formed much further out than Jupiter, as Saturn began turning inwards, it would have a profound effect on Jupiter's trajectory. As the two giants drew closer together, they became locked in an intimate gravitational dance, an orbital resonance that meant that for every orbit Saturn made around the Sun, Jupiter made 2 circuits, exerting a regular periodic gravitational influence on each other as the two giant worlds passed close by. The result of this orbital resonance between Jupiter and Saturn cleared out all of the gas and dust between the two planets, creating a gap in the disk of the early solar system. And this interaction between the two resonant planets and the gas and dust at the edge of the gap resulted in both planets changing tack. The orbits of both Saturn and Jupiter began to move outwards, away from the Sun, preventing Jupiter from moving any further into the inner solar system. Earth was given a reprieve, and Jupiter was dragged back out into the asteroid belt once more. This change in direction has become known as the grand tack hypothesis, a nod to the action of a sailboat as it tacks and changes course while it travels against the direction of the wind. Just like a sailboat, the theory suggests Jupiter tacked around 1.5 AU from the Sun, in the current orbit of Mars, changing direction and pulling back out to its current orbit at 5.2 AU. It's a theory that's been driven by using advanced computer modeling, which helps to explain many of the inconsistencies between our solar system and the hundreds of other planetary systems we've recently observed. It's the grand tack that accounts for the lack of super-Earths and explains the presence of only a handful of small rocky worlds with thinner atmospheres than those observed around other stars. The grand tack also allows us to explain the unusually small size of Mars, which simulations predict should be at least half the mass of the Earth, if not bigger, rather than the 0.107 Earth's mass we find it to be. It also helps explain the odd inhabitants of the asteroid belt, transformed by Jupiter's journey not just once but twice across this region of space. This is why we see half-finished planets like Ceres and Vesta left starved of building material, and an asteroid belt that has a surprisingly small mass, with objects that appear to originate from both inside and outside Jupiter's orbit, and have a wide range of eccentric orbits themselves. Jupiter, the father of the skies and ruler of the heavens, had spread its hand far and wide, sculpting the precious solar system we see today in the space of just a few million years. Before coming to rest, though, it would grant one more precious gift to the newly forming planet Earth. As Jupiter was dragged out, crossing the asteroid belt for a second time, it encountered a region full of objects rich in water and bearing minerals, and Jupiter's trajectory caused these objects to be flung back into the inner solar system. They crashed into the young planets and moons with an intensity never seen before or since, in a period known as the Late Heavy Bombardment. It transformed the makeup of the inner solar system, delivering a large percentage of the water Earth holds on its surface today. It's extraordinary to think that it was Jupiter that was responsible for the delivery of the most important ingredient of life, the water that provided an ideal environment for life to spark and thrive in one unbroken line for the last 4 billion years. This story offers an extraordinary understanding of the power Jupiter has wielded over all of our lives. The more we learn about the formation of solar systems, and the more we try to model a system like ours with 4 terrestrial, water-rich planets close to the star and the gas giants further out, the more we learn that perhaps all these things had to happen. These unlikely movements and interactions between the planets were necessary to produce a system like ours, and a planet like ours. So if events like the tack of Jupiter are, as we believe them to be, extremely uncommon, the conditions for the formation of Earth-like planets, terrestrial worlds with plenty of liquid water beneath the gentle pressures of a thin blue line, must be exceedingly uncommon. It's a humbling thought to begin to comprehend that the Earth may not just be a rare rock in our solar system, but a rock that only exists because of the rare system of planets within which it evolved. All the evidence is beginning to suggest that we may be living on a tiny oasis within a vast desert, devoid of life and stretching out across the Milky Way. Today, Jupiter has settled into a regular orbit at the far side of the asteroid belt, its days of marauding through the solar system at an end. Established in a stable orbit for almost 4 billion years, it has looked down on our planet as a distant light in the sky, unchanging while the work of evolution by natural selection has transformed the first sparks of life on Earth into the endless, beautiful forms that we witness today. But although distant and seemingly detached, Jupiter's influence has been far from benign. The history of life on Earth has been interrupted by numerous cataclysms, impacts with asteroids that have fundamentally shifted life again and again. And the hand behind these disruptions? It's Jupiter, that has continued to hold immense sway over our planet, exerting its influence on the asteroid belt with just the smallest of nudges, the difference between existence and extinction. At 16:53 UTC on the 18th of October 1989, the Space Shuttle Atlantis took off from the Kennedy Space Center in Florida, carrying the Galileo spacecraft carefully packed away in its hold. Released into Earth's orbit from the cargo bay just a few hours later, the probe would begin a 6-year journey to Jupiter that would utilize flybys of Earth and Venus to propel it on its 4.6 million kilometer voyage across the solar system. Entering orbit around the giant planet on the 8th of December 1995, Galileo would not only become the first spacecraft to orbit Jupiter, but also the first craft to orbit any of the outer planets. It spent nearly 8 years in the Jovian system and explored the giant planet and its menagerie of moons in intricate detail for the very first time, revealing a host of new discoveries. From precise measurements of Jupiter's atmosphere and observation of its giant thunderstorms, to discovering liquid water under the surface of the moon Europa and the first detailed studies of the intense volcanic activity of Io, this was a mission that opened our eyes to the beauty and diversity of the Jovian system, in a level of detail that we could scarcely have imagined possible. But long before Galileo even arrived, this 2-ton explorer would already have changed our view of the solar system. Entering the asteroid belt in August 1991, Galileo performed the first close-up flyby of an asteroid, passing within 1,500 kilometers of 951 Gaspra, and returning the first detailed images of this rocky remnant back to Earth. Its next close encounter would come almost 2 years later, when flying past 243 Ida, the probe discovered that this asteroid had its own moon. Dactyl, as it has become known, was the first asteroid moon ever to be discovered, and the images are beautiful. A tiny 1.5 kilometer wide object in a chaotic orbit around its parent rock. After this unexpected encounter, Galileo continued its long journey across millions of kilometers of empty space, still 4 years away from its ultimate rendezvous with Jupiter. But by luck rather than judgment, this tiny probe happened to be traveling towards Jupiter at the precise moment it would be able to witness one of the rarest of shows our solar system has to offer. On the night of the 24th of March 1993, as Galileo sped across the solar system, 3 astronomers working at the Palomar Observatory in California were attempting to spot and track what are known as near-Earth objects, undetected meteors that might be of potential threat to our planet. That evening, David Levy, along with Carolyn and Eugene Shoemaker, took a series of images using the 1.5-foot Schmidt telescope. Lurking in one of them was an unusual artifact that grabbed the attention of the team. Streaking across the image was an object that, although nowhere near the Earth, was of immediate and immense interest. A comet that appeared not only to be unusually close to Jupiter, but also seemed to have multiple nuclei, a fragmented series of rocks trailing across 1 million kilometers of space. In a moment of wondrous astronomical serendipity, the team had discovered the first ever comet in orbit around another planet. a comet that had not only been captured by Jupiter's immense gravity, but had also been pulled apart by it. Shoemaker-Levy 9, as it became known, because it was the 9th comet this team had found, was a comet unlike anything we'd seen before. Quickly confirmed by further studies to be orbiting Jupiter, and thought to have been captured from its solar orbit back in the late 1960s or early 1970s, astronomers were able to wind back through its orbital history and calculate the precise moment the comet was ripped apart. Passing just over 40,000 kilometers above Jupiter's cloud tops on the 7th of July 1992, we think Shoemaker-Levy 9 fell within the planet's Roche limit, and this 5-kilometer comet was ripped apart by the huge tidal forces generated this close to the planet. It disintegrated into 23 pieces visible to us here on Earth, labeled fragments A to W, with the biggest up to 2 kilometers in diameter. This alone was a remarkable discovery, a visual representation of Jupiter's colossal gravitational power. But if that wasn't enough, it quickly emerged from orbital calculations that the comet seemed to be on a trajectory that would ultimately take it straight through the center of the planet. Shoemaker-Levy 9 was on a collision course with Jupiter, and as if we had scheduled it ourselves, the date of the predicted impact was July 1994. Perfect timing for the spacecraft we already had en route. By the beginning of July 1994, Galileo was 238 million kilometers from Jupiter, on the very edge of the asteroid belt and speeding through space towards its final destination. Ahead of it, comet Shoemaker-Levy 9 was entering its final few days in orbit around the planet. With the first impact expected on the 16th of July, the world's most powerful terrestrial telescopes were trained here, as well as some of our space observatories, from the newly fixed Hubble Space Telescope to the Ulysses spacecraft, which turned its gaze from its primary job of watching the Sun. Even the distant Voyager 2 probe, 6.6 billion kilometers away beyond Neptune, was able to look for radio wave emissions from the impact and employ its ultraviolet spectrometer to make distant observations. But for all of this technology peering across the solar system, there was only one set of eyes that would be able to see the actual first impact. The comet would first hit Jupiter on the side turned away from the Earth, but Galileo was approaching on the night side of the planet, which would give us a unique view not visible from Earth of our first ever observation of a collision between two objects in the solar system. The first impact occurred at 2013 UTC on the 16th of July, when fragment A entered Jupiter's southern hemisphere traveling at 60 kilometers a second, hitting the planet with an estimated force of 300 million atomic bombs. With its instruments trained on the impact, Galileo recorded the subsequent fireball, which reached temperatures of over 24,000 degrees Kelvin, creating huge plumes that stretched over 3,000 kilometers high. It was a breathtaking spectacle that quickly came into view from Earth as the rapid rotation of Jupiter brought the impact sites into clear sight, revealing a huge, dark spot on the surface. Over the next 6 days, 21 distinct impacts were observed, as each of the fragments impacted with its own distinct set of characteristics. Fragment G was the largest of all the impacts. Striking Jupiter on the 18th of July, it created a vast scar on the surface of the planet, stretching over 12,000 kilometers across. This extraordinary spectacle continued until the 22nd of July, when fragment W brought the show to a close, leaving just the scars of the impacts to slowly fade away over the following months. Galileo had given us a ringside seat for this rarest of phenomena. Aided by our technological eyes and ears on Earth and across the solar system, we were able not only to witness a collision like this for the very first time, but also to harvest a vast amount of data. It transformed our understanding of the composition and atmospheric dynamics of Jupiter, allowed us to precisely measure the actual size and composition of the comet itself. But perhaps most important of all, it enabled us to study a cosmic collision firsthand, revealing one of the most important dynamics of Jupiter and the power it exerts over every object and planet in the solar system, including Earth. Before it fragmented, Shoemaker-Levy 9 was at least 2 kilometers wide and weighed over 800 million tons. travelling through the solar system in an orbit that would have taken it hurtling through the inner terrestrial planets, and perhaps even close to Earth. If such an object had hit us, the consequences would have been devastating, sending a vast amount of dust and debris into the air, creating a global smog that would have darkened the planet and cooled the atmosphere, leading to a catastrophic impact on all life on Earth. We will never know whether Shoemaker-Levy would have posed a real danger to our planet, but we do know that Jupiter removed the threat, and such acts of planetary protection are not unusual. The impact of this comet demonstrated in spectacular fashion the role of Jupiter as a cosmic vacuum cleaner. Using its vast gravitational power to capture objects like SL9, by bringing them into its orbit and incinerating them on impact, we think Jupiter acts as the grand protector, luring in objects that might otherwise pose a threat of collision with the Earth. But as we have so often seen with the story of Jupiter, no act is ever truly benevolent. For every potentially dangerous object it shields us from, it can throw another in our direction. That's because of the influence it exerts over all the objects in the asteroid belt. It's easy and quite natural to think of the asteroid belt as a single homogeneous structure, a ring of rocks orbiting in an orderly fashion around the Sun. But it's nothing like that at all. In reality, each of the millions and millions of pieces of rock is following its own individual orbit, distorted and eccentric orbits that create what appears to be a chaotic cavalcade around the Sun. But although there are complex patterns, there is also structure, and nothing has more influence on that structure than Jupiter, the silent conductor of the asteroid belt. In some way, every asteroid dances to Jupiter's tune, whether it's the Trojan asteroids orbiting ahead of and behind Jupiter, or the Hilda asteroids that orbit around in three groups, due to the delicate interplay between the gravitational pull of the Sun and that of Jupiter. Every asteroid is in some way caught between the two largest objects in the solar system. In such a chaotic, complex system, collisions between asteroids are inevitable, and disturbances to an orbit are commonplace. All it takes is for an asteroid to line up with Jupiter, and the resultant gravitational kick it receives can send an asteroid hurtling outwards, banishing it to the far edges of the solar system, or inwards towards the inner planets. It's by this mechanism that Jupiter continues to exert its influence across every corner of the solar system. Over the last 4 billion years, from its distant orbit 778 million kilometers away from the Sun, Jupiter has repeatedly played with the destiny of our planet and the path of life upon it. The surface of the Earth is strewn with the evidence of cataclysmic collisions that have significantly shaped the history of the planet. From the delivery of huge volumes of water almost 4.5 billion years ago, to the near planet-destroying events of the late heavy bombardment, and even the formation of the Earth-Moon system. All of these momentous events can be linked to the shifting influence of Jupiter and its gravitational stranglehold on objects across the solar system. Over millions of years, the evidence for many of these collisions has been lost or hidden under the ever-changing surface of our planet. But as we've been able to see at impact sites like the Barringer crater, Jupiter's hand is never far away from shaping events on the surface of Earth. The discovery of one such impact crater underneath the Yucatan Peninsula in Mexico back in the late 1970s has revealed evidence of an event that in a single moment changed the course of life on Earth perhaps more profoundly than any other, transforming the very possibility of our own existence. Around 66 million years ago, in the far reaches of the asteroid belt, an object at least 15 kilometers wide was making its final orbit of the Sun. Just one asteroid among millions, this insignificant object had been following the same path for millions, if not billions of years. But then, something changed. Exactly what caused it to alter its path will never be known. But the most likely explanation is that a gravitational nudge from Jupiter pulled it out of its innocuous orbit and sent it on a very different trajectory, a direction that would ultimately bring it on a collision course with Earth. Traveling through space, it would have descended through our atmosphere in just a few seconds, before striking the Earth with a force equivalent to 100 million megatons of TNT. The impact generated a fireball so hot that anything within a 1,000-kilometer radius was instantly vaporized, leaving a crater 180 kilometers wide and 20 kilometers deep. Today, the town of Chicxulub sits near to what we think is the center of the impact site, and lends its name to the crater that stretches out west onto the Yucatan Peninsula and east into the Gulf of Mexico. The evidence for this giant impact doesn't just sit in the partially hidden Chicxulub crater, but also in a thin layer of sediment found throughout the world that contains unusually high levels of iridium. This metal is exceptionally rare in the Earth's crust, but is found in abundance within asteroids. So we believe its presence in the thin layer of sedimentary rocks around the globe dating back 66 million years ago is a direct remnant of the huge rock that struck the Earth. This geological signature is known as the KPG boundary because it marks not just the impact itself, but a boundary between two epochs of life on Earth, the end of the Cretaceous period and the beginning of the Paleogene. It was an event that lasted just a few seconds, but in the aftermath of the impact, millions of tons of sulfurous rock were thrown up into the atmosphere, and during the nuclear winter that followed, 75% of all species were wiped from the face of the Earth, including the largest creatures ever to walk the planet. In a global extinction event that affected every continent simultaneously, the age of the lizards was brought to an end, as almost every species of dinosaur, and many other species as well, vanished in the space. According to Steve Desch, professor of Earth and Space Exploration at Arizona State University, it was an event we would not like to see the likes of again. If something the size of the Chicxulub impactor that killed the dinosaurs were to happen today, it would just be utterly catastrophic for mankind. The most immediate thing is you would have a magnitude 13 earthquake, and then you would have tidal waves that could happen anywhere near water that are miles high, propagating out for thousands of miles in every direction, and that's just for starters. Eventually, so much dust would be kicked up into the atmosphere, it would block sunlight, destroy agriculture, our infrastructure would fail. Today, just traces of the dinosaurs remain. These creatures that ruled the Earth are now nothing more than a dusty history captured in the fossil record. One event, one asteroid, one orbit that was changed by the might of Jupiter. Without the distant planet's intervention, it's possible that those giant lizards might still be here today, and the evolutionary niche that opened up for us with their removal might never have appeared. There are many chance events, not only throughout the history of Earth, but also spanning the entire history of the universe for 13.8 billion years, without which we wouldn't exist. There's an unbroken chain of life stretching back 4 billion years here on this planet. But having said that, there are major events that affected life, and one of them, without doubt, is the asteroid that wiped out the dinosaurs. And so, in that sense, it is true to say that without Jupiter, we wouldn't be here. The godfather of the planets paved the way for humankind to inherit the Earth, and it has looked down on us benevolently ever since, using its immense power to keep us safe. A sleeping giant with its power undiminished. An asteroid impact like the one that cleared the way for us to evolve 65 million years ago would have catastrophic consequences for our civilization, were something similar to strike today. To the naked eye, Jupiter is one of the brightest points of light in the night sky, and through a small telescope it is a beautiful, banded world. It feels distant, eternal, disconnected from events here on Earth. But the more we've learnt about the history of the solar system, the more we've come to understand that that is not the case. Jupiter has played an important and perhaps decisive role in the stories of all the planets, including Earth. You see, the solar system is just that. It's a system, complex, interconnected, and interdependent. So the next time you see Jupiter, just hold your gaze and think for a while about the fact that it is so much more than a point of light, or a planet even. Jupiter is the great sculptor of the solar system, the destroyer and creator of worlds.
What is science? There are many answers, and whole academic careers are devoted to a complex analysis of the historical and sociological development of the subject. To a working scientist, however, I think the answer is quite simple and illuminating, because it reveals a lot about how scientists see themselves and what they do. The great and overused adjective, but not in this case, physicist Richard Feynman gave a characteristically clear and simple description in his Messenger lectures delivered at Cornell University in 1964.
In general, we look for a new law by the following process. First, we guess it. Then we... Now don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, to see what it would imply. And then we compare the computation results to nature, or we say compare to experiment or experience, compare it directly with observations to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make any difference how beautiful your guess is. It doesn't make any difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Why do I like this so much? The reason is that it's modest, almost humble in its simplicity, and this, in my opinion, is the key to the success of science. Science isn't a grandiose practice. There are no great ambitions to understand why we are here, or how the whole universe works, or our place within it, or even how the universe began. Just have a look at something, the smallest, most trivial little thing, and enjoy trying to figure out how it works. That is science.
In a famous BBC Horizon film broadcast in 1982 called The Pleasure of Finding Things Out, Feynman went further. People say to me, "Are you looking for the ultimate laws of physics?" No, I'm not. I'm just looking to find out more about the world, and if it turns out there is a simple ultimate law which explains everything, so be it. That would be very nice to discover. If it turns out it's like an onion with millions of layers and we're just sick and tired of looking at the layers, then that's the way it is. My interest in science is to simply find out more about the world. The remarkable thing about science, however, is that it has ended up addressing some of the great philosophical questions about the origin and fate of the universe and the meaning of existence, without actually setting out to do so. And this is no accident. You won't discover anything meaningful about the world by sitting on a pillar for decades and contemplating the cosmos, although you may become a saint. No, a truly deep and profound understanding of the natural world has emerged more often than not from the consideration of much less lofty and profound questions. And there are two reasons for this. Firstly, simple questions can be answered systematically by applying the scientific method as outlined by Richard Feynman, whereas complex and badly posed questions, such as why are we here, cannot. But more importantly, and rather more profoundly, it turns out that the answers to simple questions can overturn centuries of philosophical and theological pontificating quite by accident. Reputations count for naught in the face of observation. The famous story of Galileo's clashes with the Inquisition at the height of the Copernican debate, which he certainly did not expect, nobody does, is the archetypal example. Galileo began his university career with the study of medicine, but his imagination was captured by art and mathematics. Between studying medicine in Pisa and returning to his hometown in 1589 to become professor of mathematics, Galileo spent a year in Florence teaching perspective, and in particular a technique called chiaroscuro. Chiaroscuro is the study of light and shadow, and how it can be used to create a sense of depth by accurately representing the way that light sources illuminate objects. Chiaroscuro was one of the most important new artistic techniques to emerge during Galileo's time, allowing a new sense of realism to be portrayed on canvas. Although Galileo spent only a brief time in Florence, the skills he acquired had a great impact on his scientific work. In particular, his carefully developed ability to understand the delicate play of light on three-dimensional shapes, when applied to his later astronomical studies,
played an important role in undermining the Aristotelian cosmological edifice, which formed a cornerstone of the teachings of the Roman Catholic Church. The small and seemingly innocuous theological thread on which Galileo unwittingly tugged was made available to him on a visit to Venice in 1609, when he purchased the lenses required to build his first telescope. One of the first objects he turned his perspective tube towards was the moon. With the mind of a mathematician and the eye of an artist, Galileo drew a series of 6 watercolors representing what he saw. These images are both beautiful and revolutionary. Catholic dogma asserted that the moon and the other heavenly bodies were perfect, unblemished spheres. Previous astronomers who had viewed the moon either with the naked eye or through telescopes had drawn a 2-dimensional blotchy surface, but Galileo saw the patterns of light and dark differently. His training in chiaroscuro revealed to him an alien lunar landscape of mountain ranges and craters. I have been led to the conclusion that the surface of the moon is not smooth, even, and perfectly spherical, as the great crowd of philosophers have believed about this and other heavenly bodies, but on the contrary, to be uneven and rough, and crowded with depression and bulges. And it is like the face of the earth itself, which is marked here and there with chains of mountains and depths of valleys. Galileo shared the watercolors with his long-standing friend from Florence, the artist Cigoli, who was inspired to represent this new and radical view of the moon in the grandest of settings. Built in the year 430 by Pope Sixtus III, the Pauline Chapel in Rome documents the changing artistic styles and techniques used to represent the natural world across many centuries. A place filled with shifting examples of how the 3-dimensional world can be represented on a 2-dimensional surface. Covering the dome of the Pauline Chapel is Cigoli's final masterpiece, a striking fresco depicting a familiar scene of the Virgin Mary bathed in a shaft of golden light surrounded by cherubs and angels. The fresco depicts Mary over what was, for the first time, a detailed, textured, and cratered moon. The Vatican named it the Assumption of the Virgin, unaware perhaps of the philosophical challenge it represented. Here was art representing scientific knowledge, a type of knowledge radically different from historical or scriptural authority, based on observation rather than dogma, and presented unashamedly in a grand setting for all in Rome to see. It is undoubtedly true that Galileo didn't intend to challenge the very theological foundations of the Church of Rome by observing the moon through a telescope. But scientific discoveries, however innocuous they may seem at first sight, have a way of undermining those who don't much care for facts. Reality catches up with everyone eventually. With his depictions of the moon completed, Galileo turned his ever more powerful lenses to other celestial bodies. Between the 7th and the 13th of January 1610, he became the first human to observe Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, now known as the Galilean satellites. For Galileo, this was further evidence to support the work of Copernicus and the physical reality of the heliocentric model. If moons were orbiting Jupiter, Galileo reasoned, it was impossible to argue that the Earth was at the center of the universe, because heavenly bodies existed that did not circle the Earth. Galileo published these observations in the spring of 1610 in The Starry Messenger, and from his correspondence with Kepler, his irritation with the discontent it caused amongst philosophers was clear. "My dear Kepler, I wish that we might laugh at the remarkable stupidity of the common herd. What do you have to say about the principal philosophers of this academy, who are filled with the stubbornness of an asp and do not want to look at either the planets, the moon, or the telescope, even though I have freely and deliberately offered them the opportunity 1,000 times? Truly, just as the asp stops its ears, so do these philosophers shut their eyes to the light of truth." To Galileo's mind, absolute confirmation of Copernicus's heliocentric model was provided by his studies of Venus. Beginning in September 1610, Galileo observed Venus over the course of months, and like the Moon, he observed that Venus had phases. Sometimes the planet was lit completely by the Sun, but at other times only a crescent appeared to be illuminated. The only plausible explanation for this observation was that Venus was orbiting the Sun. This was surely final, compelling evidence of a solar system with the Sun at its heart, and the planets orbiting around it. It wasn't that simple, of course. Galileo, in what was certainly an ill-judged move, decided to move beyond reporting his scientific observations and instead champion a particular theological and philosophical interpretation of the data, namely that the Church was wrong and that the Earth was most definitely not the center of the universe. This he seems to have done because he wanted to be famous, and famous he became. Copernicus's De Revolutionibus was banned until corrected. The full version was not removed from the banned list until 1758, and Galileo ordered not to repeat his foolish and absurd conclusions. Galileo didn't keep quiet, and he achieved his historical notoriety by being put under house arrest in 1633, where he stayed for the remainder of his life. Many historians characterize Galileo as a bit of an egotistical social climber who brought it all on himself, which is partly true, and yet also desperately unfair. He was undoubtedly a great scientist and a supremely talented astronomical observer. In particular, he was the first to clearly state the principle of relativity which lies at the heart of Newton's laws of motion, namely that there is no such thing as absolute rest or absolute motion. This is why we don't feel the movement of the Earth around the Sun, and why Aristotle et al. Were misled into reading far too much into their stationary feelings. In the hands of Albert Einstein, the principle of relativity can be generalized to freely falling objects in a gravitational field, and this ultimately leads to modern cosmology and the Big Bang theory. But we are jumping ahead again. The purpose of recounting the story of Galileo is not to attack the easy target of the Inquisition, which nobody expects. Rather, it is to highlight the fact that the smallest and most modest of scientific observations can lead to great philosophical and theological shifts that in turn can have a tremendous impact on society. Galileo, by looking through a telescope, doing some drawings, and thinking about what he saw, helped to undermine centuries of autocratic idiocy and woolly thinking. In doing so, he got himself locked up, but also bridged the gap between Copernicus and Kepler, and paved the way for Isaac Newton, and ultimately Albert Einstein, to construct a complete description of the universe and our place within it.
In a little over 6 decades, we've met every one of the planets in our solar system. Traveling at first to our nearest neighbors, we visited Venus, Mars, and Mercury, and found rocky planets covered with the remains of long-lost worlds. Each has a life that followed very different paths. To these planets we returned time and again, staying longer on each visit, exploring deeper, and even touching down onto alien ground. Then we ventured further, beyond the rocky worlds, beyond the ice line, and out to the land of the giants. As we explored Jupiter and Saturn, we began to piece together the extraordinary life story of these gas giants, and all the exotic moons in their grasp. But that was just the beginning. Beyond Saturn, out there far into the darkness, lie the most distant planets of the solar system, worlds we can hardly even glimpse from Earth. Uranus, a pale blue marble hanging in the frozen depths of space. Further out, its icy sibling Neptune, and beyond that Pluto, a world but not a planet, which until now has remained virtually hidden from us in all but name. Each lies not millions but billions of kilometers from Earth, and for this reason only once have we dared to visit them and capture a set of images from the dark. Precious data that allows us to begin to understand the endless mysteries that lie out there, at the outer edges of our solar system and beyond. The scale of the solar system is virtually unimaginable. a landscape laid out across distances impossible to comprehend within the realms of human experience. London to New York is 5,500 kilometres. London to Sydney a mere 17,000 kilometres, while London to the Moon is 384,000 kilometres, and the longest single journey any human has ever completed, the equivalent of travelling 9.5 times around the circumference of Earth. Beyond these journeys, as we look out towards ever more distant destinations, the numbers grow so big so quickly that we've had to invent a different unit of distance altogether in order to give us a containable scale for the vastness of the cosmos. It's based on the mean distance between the Earth and Sun, which is 149,598,000 kilometres, known as 1 astronomical unit, or 1 AU. Today we can measure this distance with relative ease, but calculating that number for the first time with any accuracy was far from an easy task. For near on 2,000 years, many a great mind took measurements, made calculations, and came up with numbers that estimated the distance to the Sun. But it wasn't until the 17th century that we were able to measure for the first time the distance to our star, when Joseph Kepler provided the mathematical underpinning and Edmund Halley the understanding that the transit of a planet could unlock our ability to accurately calculate an astronomical unit. Halley was the first to realize in 1716 that by measuring a transit of Venus, the moment our sister world passes directly between us and the Sun, from different positions around the globe, we could obtain the necessary numbers to allow the geometry to play out. Unfortunately for Halley, he had the right idea at the wrong time, as transits of Venus are enormously rare, coming in pairs approximately once every 120 years. So, in one of the great scientific baton passes of all time, Halley left behind detailed instructions for future astronomers to carry out his plan. 20 years after his death, the 1761 transit of Venus provided the first opportunity to put his theory to the test. In a remarkable combination of collaboration and competition, which occurred in the middle of the Anglo-French 7 Years' War, observers from both these countries travelled all over the world to destinations as far afield as Siberia, Madagascar, Newfoundland, and the Cape of Good Hope, praying for a clear sky to observe and measure the transit. Combined with a similar set of expeditions for the next transit 8 years later, enough data was gathered to allow the French astronomer Jérôme Lalande to calculate the distance between the Earth and the Sun for the very first time, coming up with a pretty accurate figure of 153 million kilometres. Today we no longer need to rely on the rarest of astronomical events to make these measurements. Instead, we have far more direct ways of measuring that have allowed us to plot our journey around the Sun in ever greater detail. Throughout a year, as we follow our elliptical orbit around the Sun, the distance from our planet to the centre of the solar system varies enormously. This means that in early January each year, as we reach the closest proximity to our star, known as perihelion, we are about 147 million kilometres distant. 6 months later, in early July, we reach aphelion, our furthest distance from the Sun, and find ourselves about 5 million kilometres further away, orbiting at around 152 million kilometres away. Exactly what 1 astronomical unit actually is has therefore been the subject of intense debate and change over the last century, and as we have sent our robotic explorers across the solar system, our ability to directly measure the precise distances between the inner planets using radar and telemetry has yielded endless refinements. So since 2012, we, or the International Astronomical Union on our behalf, have made life much more straightforward by defining 1 AU as 149,597,870,700 metres, or about 150 million kilometres. Mars, the furthest out of the 4 rocky planets, sits at 1.5 AU, half as far away from the Sun again as we are. At 2.2 AU, the asteroid belt begins, a swirling carousel of rocks and failed worlds. It stretches out for another 150 million kilometres before coming to an end. Here, at the snow line of our solar system, 3.2 AU away from the Sun, we leave the rocky worlds behind and continue across another 300 million kilometers of space before we reach the first of the giants, Jupiter. And yet here, at 5.2 AU, 780 million kilometers from the Sun, our journey has only just begun. It is almost double the distance again before we reach the next planet, the ringed jewel that is Saturn, sitting 9.6 AU, or 1,434 million kilometers from the center. It is here that the realm of our exploration ends, at the last of the planets that we can say we have truly explored. Mercury, Venus, Mars, Jupiter, Saturn. Each one a world that we have not only visited but resided around. Our robotic explorers orbiting with camera eyes wide open for years at a time. In many cases we've not just looked at but also touched the surface of these worlds and the moons they embrace. Once we get beyond Saturn, the scales change so much, the distances grow so vast and travel times so long, that they are measured not in days and months, but years and decades. Uranus, the first of the ice giants, sits over twice as far away from the Sun as Saturn, orbiting at an average distance of 19.2 AU, or 2.871 billion kilometers. Then Neptune, the farthest of the planets, lies another 11 AU further out, and orbits nearly 4.5 billion kilometers away from the Sun. After it comes Pluto, on the highly elliptical orbit that takes it inside and outside the line of Neptune, but on average sits 5.9 billion kilometers away from the Sun. To reach these worlds is so difficult that in our 60 years of planetary exploration we visited each only once, and spent just the briefest of moments in close proximity to them. We manage a matter of hours in each system, as our spacecraft are propelled at enormous speeds, so fast that they quickly fly past and beyond. But the precious scraps of data they have returned have allowed us to peer through the mysteries that lie out there at the outer edge of our solar system, and start to tell the extraordinary stories that reach deep into the darkness. To reach the outer planets has taken the work of perhaps the greatest of all of our planetary explorers. At the time of writing, in January 2019, the Voyager 2 spacecraft has been in continual operation for 41 years, 4 months, and 19 days. Traveling at 15.341 kilometers per second, it is currently around 119 AU from the Sun, that's 17 billion kilometers away, and has just recently been officially deemed to have entered interstellar space. No longer within the empire of our Sun, the heliosphere created by the solar wind that defines the boundary of our solar system, this little probe weighing less than a family car is the third human-made object after its sibling Voyager 1 and also Pioneer 10 to leave our home star system behind. As it heads out into the void, it is expected to continue to stay in contact with us here on Earth for at least another 6 or 7 years, transmitting its weak radio signals until at least 2025, before slipping off into its final silence around 48 years after its launch, on its way towards a small star called Ross 248, located in the northern constellation of Andromeda. The Grand Tour. It all began on the 20th of August 1977, when the Voyager 2 spacecraft left our planet on board a Titan III rocket, taking off from Launch Complex 41, Cape Canaveral Air Force Base. 2 weeks later, on the 5th of September, the twin probe Voyager 1 would follow hot on the heels of its sibling. Taking the fast lane, Voyager 1 would speed ahead, reaching Jupiter 4 months earlier than Voyager 2, which had been sent on a different trajectory that took it on a slower, longer, more circular course. Making its closest approach on the 9th of July 1979, Voyager 2 swept past Jupiter at a distance of 576,000 kilometers from the planet's cloud tops, gathering a vast amount of data on the giant planet's atmospheric characteristics and its moons. This included the first detailed analysis of the swirling storm known as the Great Red Spot, as well as a 10-hour analysis of the volcanoes of Io, allowing the activity to be calculated by directly comparing the images of the Moon with images Voyager 1 had taken just a few months before. Using Jupiter as a gravitational springboard, Voyager 2 then left the Jovian system behind and continued on a 2-year journey to Saturn. With its closest approach occurring on the 26th of August 1981, Voyager 2 became the third spacecraft to visit Saturn, providing a vast range of pictures and data on the planet, its rings and moons. But it was the next leg of its journey that would be truly groundbreaking, and it was only possible because of the rarest of celestial alignments. Back in 1964, Gary Flando, an aerospace engineer working at the Jet Propulsion Laboratory in Pasadena, California, noticed that an unusual configuration of the 4 outer planets would occur in the late 1970s and early 80s. Flando realized that this particular alignment, which occurs once every 175 years, would potentially allow a single spacecraft to visit all the outer planets using a series of flybys and gravity assists that would provide an opportunity to visit not just Jupiter and Saturn, but Uranus and Neptune for the very first time. Over the next 15 years, NASA began plotting a mission to complete what became known as the Grand Tour. Various plans for the tour were started and shelved as the costs and feasibility of the proposed route came into question, until eventually in 1972, the twin-probe Mariner-Jupiter-Saturn project was approved with an estimated cost of $360 million. The 2 probes would eventually be renamed the Voyagers, and only one would complete the Grand Tour. Voyager 1 would be sent from Jupiter to Saturn, and then on to its satellite Titan, to attempt to explore the Moon and its intriguing atmosphere. But Voyager 2 would be given the grandest of journeys, and the honor of becoming the first craft to attempt to see Uranus and Neptune close up. Flying past the Saturnian system in late August 1981, Voyager 2 began a journey into the darkness that has yet to be repeated. Over the next 3.5 years, the craft would make its lonely journey outwards towards its unique encounter with the 3rd largest planet in the solar system, a planet that until then we had only ever been able to peer at in the distance. The pale blue marble. The 7th rock from the Sun sits 2 billion kilometers from the Earth, a pale blue marble hanging faintly in our night sky. Barely visible with the naked eye, ancient observers dismissed the object as a star, too slow and too dim to join the family of planets. It wasn't until the invention of the telescope that the real character of this distant object began to emerge. But even then, the discovery of Uranus was a slow one. It began on a cold March night in 1781, Tuesday the 13th between 10 and 11 p.m. to be precise, in the townhouse garden of William Herschel. As the 43-year-old astronomer peered through his 160mm telescope, surveying the sky that night for any small stars he could bring into view, he noticed a dim object that over the course of the next few days appeared to be slowly moving, so he assumed it must be a comet. Reporting his findings to the Royal Society the following month, Herschel still seemed convinced that this was a comet, not a planet, even though he himself suggested that the characteristics of the observation were as planets are. The Astronomer Royal at the time, Neville Maskelyne, whose claim to fame as being the first person to measure the weight of the Earth scientifically for the first time, wrote to Herschel in late April 1781 to share his bafflement. "I don't know what to call it," he wrote. "It is as likely to be a regular planet moving in an orbit nearly circular to the Sun as a comet moving in a very eccentric ellipsis." Eventually, the accurate computation of the body's orbit, calculated by a number of different astronomers, provided the ultimate proof of its character, and its planetary status was confirmed by Herschel in a letter to the President of the Royal Society, Sir Joseph Banks, in 1783. "Sir, by the observations of the most eminent astronomers in Europe, it appears that the new star, which I had the honour of pointing out to them in March 1781, is a primary planet of our solar system. With that, the seventh planet was born into our story of the solar system. But naming this new arrival, the first planet to require such a decision since antiquity, was far from straightforward. The announcement of Herschel's discovery had not only impressed the world of science, but also captured the attention of the higher reaches of British society, all the way up to King George III. As a reward for his historic achievement, Herschel came under the patronage of the king to the tune of £200 a year, and moved to Windsor to allow the royal family the use of his telescopes. Herschel had the perfect response in mind to return such favours. Charged with the responsibility of naming the new planet, he proposed the name Georgium Sidus, George's star, after the king himself. However, the name met with immediate opposition away from British shores, so other more universal alternatives were proposed, including Herschel, Neptune, and Uranus, after the Greek god and father of Saturn. Amazingly, Georgium Sidus continued in some usage for the next 70 years, but by 1850, when His Majesty's Nautical Almanac Office finally caved in, the name was switched to Uranus, and it finally and permanently stuck. It would be 136 years later, across 2.6 billion kilometres of space, when the planet that was discovered in the back garden of a Somerset townhouse would slowly expand into the viewfinder of Voyager 2. Approaching it at 17 kilometres per second after a journey of over 8.5 years, our first and only close encounter with this most enigmatic of planets would play out within a matter of just 6 or so hours. Remarkably little was known about Uranus as the spacecraft began the observatory phase of its mission in early November 1985. We knew this world was the third largest by volume after Jupiter and Saturn, and that it took a leisurely 84 years to complete a single, highly elliptical orbit, but we could only estimate the length of its day to be somewhere between 16 and 24 hours. We also knew its composition was substantially different to the two gas giants, with higher amounts of water, ammonia, and methane compared with its bigger neighbours. But how this formed an atmosphere, and what dynamics played out beyond the pale blue mist, was a mystery. We also knew that it had at least 5 moons, tiny points of light in orbit that we had detected with telescopes from Earth. But again, what form these moons took and what features they held remained a complete mystery, as was a faint and narrow set of rings around the planet that had only been discovered a few years earlier. What these rings were made of, and why they had formed from such dark material compared with the glowing rings of Saturn, was yet another element that needed exploration. But perhaps the most mysterious of all was the fact that the whole Uranian system had the strangest of orientations. The planet's rotation, its moons, and its rings all appeared to be tipped up on the side, rotating around a horizontal rather than a vertical axis, in contrast with every other planet in the solar system. As astrobiologist David Grinspoon explains, the Uranian system really stands out in the solar system in several ways, but the most striking way, visually, is that it's tilted on its side, almost completely, so that the north pole of Uranus sometimes points right at the Sun, and it's always in that plane of the orbits, and the moons as well are orbiting in that extremely tilted plane, so the whole system forms this sort of bullseye pattern that is rotating at this odd angle around the Sun. At 9:59 PST on the 24th of January 1986, the spacecraft flew just over 81,500 kilometers above the cloud tops of Uranus, at its closest proximity to the target. Back on Earth, receiving stations looked up to the sky impatiently, pointing their giant antennae towards the far explorer in anticipation of the first of its faint radio signals. But for all the anticipation and expectation of a mission that had been decades in the planning, years in transit, and with a catalogue of extraordinary revelations already behind it, the first impressions were perhaps a little underwhelming. The first images returned by Voyager revealed a beautiful but featureless world, a pale blue orb hanging in the frozen reaches of our solar system that was covered in an unbroken haze, in striking contrast with the dynamic realms of Jupiter and Saturn that Voyager had revealed to us in such detailed beauty. Peering into the haze, only 10 cloud features could be seen across the whole planet, blown around by winds travelling in the same direction as the planet rotated. But despite the sameness of first appearance, slowly but surely the data that Voyager returned would change our understanding of almost every aspect of this world. Voyager was able to measure the rotation of the interior of the planet for the first time, revealing that a day on Uranus lasted for 17 hours and 14 minutes. Beyond that, it also revealed Uranus to be a bitterly cold world, with the average temperature being an icy minus 213 degrees Celsius. In fact, we now know that Uranus is the coldest planet in the solar system, and with such cold comes a stillness, the lack of internal heat helping to explain the inactivity of its atmosphere. Why Uranus's internal heat appears to be so much lower than that of the other giant planets is still poorly understood. As Voyager sped past, it also attempted to measure the composition and structure of Uranus. As expected, the most abundant ingredients in its atmosphere were found to be hydrogen, 83%, and helium, 15%, although the amount of helium was lower than many scientists had predicted. The relatively high level of methane measured in the upper atmosphere, at 2.5%, also provided an explanation for the aquamarine blue glow of the planet that we'd seen from afar for so long. But understanding more about the planet's internal structure was not quite so straightforward. At roughly 14.5 times the mass of the Earth, Uranus consists mostly of water, ammonia, and methane in the form of ices that we believe are wrapped around a rocky core. However, the exact masses that make up each of these layers and the amount of each of the individual constituents was beyond the measuring capabilities of Voyager. So even today we can still only estimate the exact makeup of the planet. However, the data returned by Voyager did result in one major change in our understanding of the planet's interior. With the knowledge that the composition of Uranus, and soon Neptune, was substantially different from the gas giants of Jupiter and Saturn, a new category of planet was defined in the 1990s from the data the spacecraft gathered. Uranus is one of 2 ice giants in our solar system, a type of planet distinct from the gas giants of Jupiter and Saturn that formed in the warmer region nearer to the Sun. We still understand relatively little about the formation of the ice giants beyond the very basic facts. What we do know is that around 4.5 billion years ago, as each of the planets was forming from the ingredients of the protoplanetary disk, Uranus found itself in a region where there was an abundance of water, methane, and ammonia, at temperatures where these volatile compounds, each with freezing points above 100 K, or minus 173 degrees Celsius, were cold enough to form the ices from which most of the planet would be built. Beyond this, we can tell relatively little about the mechanism by which either Uranus or Neptune actually formed. The detailed evidence and the computer models that have allowed us to tell the earliest beginnings of the solar system and revealed so much about the formation of the gas giants and the inner planets do not yet exist for the ice giants. We simply lack a solid understanding of the mechanism by which these planets formed, and much controversy remains around the details. Uranus's rings and moons. While there remain many mysteries out there in the darkness, Voyager did allow us to begin to piece together one of the most dramatic stories that unfolded after the formation of Uranus. As the craft sped past the planet's pale blue atmosphere, it began to explore one of the least known gems in the solar system, the rings surrounding this most distant of worlds. Unlike the shimmering rings of Saturn, these rings are so dark and faint that they're almost impossible to see from Earth. In fact, we only discovered them by accident less than a decade before Voyager arrived in the Uranian system, when in 1977 a team from the Kuiper Airborne Observatory noticed a star that was briefly disappearing from view around the planet. The conclusion they came to was that the star was being occluded by a ring system. At first they confirmed 5 rings, but they increased this number to 9 after further observation. Voyager was able to image all 9 of the rings in the system, sending back extraordinary images of these dark, delicate structures, and also discovering 2 other faint rings in the process. But as well as giving us our first detailed view of the rings, Voyager added to their mystery. Made up of a combination of boulders and dust, the reflectivity of the substance of the rings as measured by Voyager was found to be incredibly low. The reason why these rings were so difficult to detect from Earth was that, unlike the glistening ice that dazzles in the rings of Saturn, the rings of Uranus turned out to be grey and made of an extremely dark material, making the spectral analysis of them extremely difficult, if not impossible. Despite the spacecraft's close proximity, we were unable to make any measurements of the constituents of the rings, and over 30 years after our only close encounter, we still don't know precisely what they're made of or where they came from. Our best guess is that they're made of ice and some other dark substance, perhaps even organic compounds that have darkened over time. The most likely scenario is that, just as with the rings of Saturn, Uranus is surrounded by the debris of a moon, a world that once orbited her and that is now broken into the millions of fragments of the rings. The rings are also extremely delicate and thin, an ephemeral set of structures that appear to defy the laws of nature. We would expect the particles to endlessly collide and the rings to spread out and begin to disperse over time, a process that should be driven by the particles on the inside of the rings being drawn into the planet by its great mass. But that doesn't seem to be happening. Something seems to be holding the rings in place. Hidden in the images taken by Voyager 2, we found a surprising answer. The outer ring, Epsilon, is the brightest and densest of all the structures in the system, and its width varies from 20 kilometers at its narrowest to just under 100 kilometers at its widest. This fragile structure is also thought to be unimaginably thin. We've never been able to measure its depth precisely, but we think it could be little more than 150 meters deep. Maintaining this delicate structure in the hostile environment around the giant planet is the job of 2 tiny moons, Cordelia and Ophelia, whose existence was first discovered from images taken by Voyager 2. With a radius of just 21 kilometers, Ophelia sits on the outside of the ring, while the slightly smaller Cordelia, the innermost known moon of Uranus, sits on the inside of the Epsilon ring. Together, these 2 moons exert a profound influence on the structure and stability of the ring they embrace. These shepherd moons quite literally guide the movement of objects around the edge of the ring, helping to maintain the sharply defined border that we've seen so vividly from Voyager's images. Simple orbital mechanics dictate that a moon or a ring particle that is orbiting close to the planet is moving more slowly than a moon or a ring particle that's orbiting further away, which means that Ophelia must be moving faster than the ring particles and Cordelia more slowly. That difference in speed is significant, because if there's a particle in the Epsilon ring that shifts for any reason, maybe it has a collision, loses a bit of energy, starts to drop down, then Cordelia will tend to accelerate that particle back up into the ring again, speeding it up by its gravitational influence. Whereas if there's a particle on the outer edge of the Epsilon ring that gets a bit more energy and rises in altitude, Ophelia tends to slow it down, and so it falls back into the ring again. It's by this mechanism that these shepherd moons keep the ring neat and tidy, and although Voyager only discovered 2 such moons on its brief flyby of the system, we can assume from the structure of the other rings that somewhere out there in the dark there are other hidden shepherds, silently keeping order amongst the rocks and dust of their flock. These 2 are just the beginning of Uranus's system of satellites. As of today, we have discovered 27 moons around Uranus, all of which are named after characters from the works of Shakespeare or Alexander Pope. This tradition began in 1852, when John Herschel, the son of William, discoverer of Uranus, named the first 2 moons after Oberon and Titania, fairies from A Midsummer Night's Dream. The 27 moons are divided into 3 categories. 13 inner moons, including the 2 innermost, Cordelia and Ophelia, are all small dark bodies that are entwined within the ring system and may even share an origin with the substance of the rings. Then, much further out, lie 9 irregular moons, ranging in size from 120 to 200 kilometers in diameter, These are almost certainly captured objects that have succumbed to the attraction of the planet's gravity. In between this rabble of objects and inner moons, we find the 5 major moons of Uranus, the only Uranian satellites we knew of before Voyager gave us a closer look. The smallest of the set is the ice moon Miranda, a strange-looking, jagged world with a diameter of 470 kilometers. It's one of the smallest objects we have studied in the solar system that has reached hydrostatic equilibrium, or in other words, is rounded by its own gravity. To look at Miranda is to see one of the most rugged landscapes in the solar system, a world of extreme geological features carved into its icy surface. And it's here that we find the highest cliff face. Verona Rupes is reckoned to be 20 kilometers in height, and it's been estimated that in Miranda's low gravity, it would take 12 minutes to fall from the top to the bottom of it. The other 4 large moons around Uranus are less visually striking. All are thought to be constructed around a rocky core surrounded by a mantle of ice. But these worlds are far from simple frozen lumps of rock. They all show signs of having been geologically active at some stage in their distant past. Dark worlds in the distant solar system that have surfaces shaped by volcanism. Ariel has a bright and seemingly young surface, paved over with recent and extensive flows of icy material in between the fault lines on its surface. Titania is also covered with huge geological faults and canyons, suggesting this too was a tectonically active world at some time in its history. With darker and potentially older-looking features, Umbriel or Oberon seem to be less active, or certainly less active in recent times. Voyager 2 gave us our first chance to explore and understand the rings and moons of Uranus. But it was as the spacecraft widened its gaze that we were able to see in detail how this whole system is set in the most bizarre of orientations. From our distant observations, we had long thought that Uranus spun on its side, but to see the whole Uranian system up close for the first time made it clear that something very different had happened in Uranus's past to set it apart from every other planet. Uranus spins on its side with an axial tilt of 97.77 degrees, resulting in one of its poles facing towards the Sun at any one time. The rings and moons are all orientated along this plane too, so the whole system orbits the Sun like a giant heavenly bullseye. We don't know for certain why Uranus is tipped over on its side, but it seems likely that at some point in the distant past it was hit by another planet at least as large as the Earth, which quite literally knocked the planet over. Backed up by modern computer simulations, it is entirely feasible that such an impact would cause the rest of the system to follow, ending up with a planet, its moons and rings, corkscrewing around the Sun. The origin of Uranus still remains for the most part unknown, and the exact reason for this eccentric orientation remains one of the great mysteries of the solar system. Voyager 2 left us with as many questions as answers, and when its encounter with Uranus officially came to an end with the firing of its thrusters on the 25th of February 1986, we left the planet and its secrets behind. 30 years later, we still have no plans to return. Our first and only close encounter with Uranus may have lasted for just a few hours, but it returned thousands of precious images and data. We had already gone further than ever before, and as Voyager left Uranus behind it, it had ahead of it a lonely 1.6 billion exploring the frozen region. It would take 3 more years before Voyager 2 would be the first instrument to achieve the larger planetary stop on its ground toward the Sun. From a distance of over 57 million kilometers, our first images of this planet began to slowly come into view in early June 1989. The near featureless orb of suddenly Uranus none emerged from dark and tiny skin. And it was immediately apparent that the moon taking 246 minutes. Early images sent back to the stars more than that Invisible to the naked eye, Neptune was a world hidden from view. Even through the most powerful of telescopes, it appeared as no more than a blurry ball of blue and green. The fourth largest planet in the solar system by volume, and the third largest by mass. From afar, we knew nothing of its atmosphere or its structure, and had only faintly observed two of the moons in its orbit, Triton and Nereid. This was a planet that had remained very firmly in the darkness, a distant world that had clung on tightly to its secrets for over 140 years. Even the discovery of Neptune played out in the darkness. The last of the planets to be discovered, it is the only one whose existence we predicted before it was ever observed by the human eye. For centuries we stared at it without knowing what we were looking at.
Scientific progress, then, is often triggered by rather innocuous discoveries or simple realizations. There's a terrible cliché about scientists exhibiting a childlike fascination with nature, but I can't think of a better way of putting it. The sense in which the cliché rings true is that children are occasionally in the habit of focusing on a very small thing and continuing to ask the question, why, until they get an answer that satisfies their curiosity. Adults don't seem to do this as much. Good scientists do, however, and if I have a thesis in this chapter, then it is as follows. By focusing on tiny but interesting things with honesty and clarity, great and profound discoveries are made, often by flawed human beings who don't initially realize the consequences of their investigations. The absolute archetypal example of such an approach can be found at the beginning of Einstein's quest to replace Newton's theory of gravity. Einstein is most famous for his equation E=mc², which is contained within the special theory of relativity he published in 1905. At the heart of the theory is a very simple concept that dates all the way back to Galileo. Put simply, there is no way that you can tell whether you are moving or not. This sounds a bit abstract, but we all know it's true. If you're sitting in a room at home listening to this book, then it feels the same as if you are sitting in an aircraft listening to this book, as long as there is no turbulence and the aircraft is in level flight. If you aren't allowed to look out of the window, then nothing you can do in the room or on the plane will tell you whether or not you are sitting still or moving. You might claim that your room is self-evidently not moving, whereas a plane obviously is, because otherwise it wouldn't take you from London to New York. But that's not right, because your room is moving in orbit around the Sun, and indeed it is spinning around the Earth's axis, and the Sun itself is in orbit around the galaxy, which is moving relative to other galaxies in the universe. Einstein discovered his famous equation E=mc² by taking this seemingly pedantic reasoning seriously and asserting that no experiment you can ever do, even in principle using clocks, radioactive atoms, electrical circuits, pendulums, or any physical object at all, will tell you whether or not you are moving. Anyone has the absolute right to claim that they are at rest, as long as there is no net force acting on them causing them to accelerate. You are claiming it now, no doubt, if you are listening to this book sitting comfortably on your sofa. Pedantry is very useful sometimes, because without Einstein's theory of special relativity, we wouldn't have E=mc², we wouldn't really understand nuclear or particle physics, how the sun shines, or how radioactivity works. We wouldn't understand the universe. Something important bothered Einstein after he published his theory in 1905, however. Newton's great achievement, the all-conquering universal law of gravitation, did not fit within the framework of special relativity, and therefore one or the other required modification. Einstein's response to this problem was typically Einsteinian. He thought about it very carefully, and in November 1907, while sitting in his chair in the patent office in Bern, he found the right thread to pull. Looking back at the moment in an article written in 1920, Einstein described his idea with beautiful and indeed childlike simplicity. Then there occurred to me der glücklichste Gedanke meines Lebens, the happiest thought of my life, in the following form.
The gravitational field has only a relative existence, in a way similar to the electric field generated by magnetoelectric induction. Because for an observer falling freely from the roof of a house, there exists, at least in his immediate surroundings, no gravitational field, his emphasis. Indeed, if the observer drops some bodies, then these remain relative to him in a state of rest or of uniform motion, independent of their particular chemical or physical nature. In this consideration, the air resistance is, of course, ignored. The observer therefore has a right to interpret his state as at rest. I am well aware that you might object quite strongly to this statement because it appears to violate common sense. Surely an object falling under the action of the gravitational force is accelerating towards the ground and therefore cannot be said to be at rest. Good, because if you think that, then you're about to learn a valuable lesson. Common sense is completely worthless and irrelevant when trying to understand reality. This is probably why people who like to boast about their common sense tend to rail against the fact that they share a common ancestor with a monkey. How then to convince you that Einstein was, and indeed still is, correct? Most of the time, books are better at conveying complex ideas than television. There are many reasons for this, some of which I'll discuss in a future autobiography when my time on TV is long over. But when done well, television pictures can convey ideas with an elegance and economy unavailable in print. Human Universe contains, I hope, some of these moments, but there is one sequence in particular that I think fits into this category. NASA's Plum Brook station in Ohio is home to the world's largest vacuum chamber. It is 30 meters in diameter and 37 meters high, and was designed in the 1960s to test nuclear rockets in simulated spacelike conditions. No nuclear rocket has ever been fired inside. The program was cancelled before the facility was completed. But many spacecraft, from the Skylab nose cone to the airbags on Mars landers, have been tested inside this cathedral of aluminium. To my absolute delight, NASA agreed to conduct an experiment using their vacuum chamber to demonstrate precisely what motivated Einstein to his remarkable conclusion. The experiment involves pumping all the air out of the chamber and dropping a bunch of feathers and a bowling ball from a crane. Both Galileo and Newton knew the result, which is not in question. The feathers and the bowling ball both hit the ground at the same time. Newton's explanation for this striking result is as follows. The gravitational force acting on a feather is proportional to its mass. We've already seen this written down in Newton's law of gravitation. That gravitational force causes the feather to accelerate according to Newton's other equation, F equals ma. This equation says that the more massive something is, the more force has to be applied to make it accelerate. Magically, the mass that appears in F equals ma is precisely the same as the mass that appears in the law of gravitation, and so they precisely cancel each other out. In other words, the more massive something is, the stronger the gravitational force between it and the Earth, but the more massive it is, the larger this force has to be to get it moving. Everything cancels out, and so everything ends up falling at the same rate. The problem with this explanation is that nobody has ever thought of a good reason why these two masses should be the same. In physics, this is known as the equivalence principle, because gravitational mass and inertial mass are precisely equivalent to each other. Einstein's explanation for the fact that both the feathers and the bowling ball fall at the same rate in the Plum Brook vacuum chamber is radically different. Recall Einstein's happiest thought. Because for an observer falling freely from the roof of a house, there exists no gravitational field. There is no force acting on the feathers or the ball in free fall, and therefore they don't accelerate. They stay precisely where they are, at rest relative to each other. Or, if you prefer, they stand still because we are always able to define ourselves as being at rest if there are no forces acting on us. But you are surely asking, how come they eventually hit the ground if they are not moving because no forces are acting on them? The answer, according to Einstein, is that the ground is accelerating up to meet them and hits them like a cricket bat. But, you must be thinking, I'm sitting on the ground now and I'm not accelerating. Oh yes, you are, and you know it because you can feel a force acting on you.
It's the force exerted by the chair on which you may be sitting or the ground on which you are standing. This is obvious. If you stand up long enough, then your feet will hurt because there is a force acting on them. And if there is a force acting on them, then they are accelerating. There's no sleight of hand here. The very beautiful thing about Einstein's happiest thought is that once you know it, it's utterly obvious. Standing on the ground is hard work because it exerts a force on you. The effect is precisely the same as sitting in an accelerating car and being pushed back into your seat. You can feel the acceleration viscerally. And if you switch off your common sense for a moment, then you can feel the acceleration now. The only way you can get rid of the acceleration, momentarily, is to jump off a roof. This is wonderful reasoning, but of course it does raise the thorny question of why, if there is no such thing as gravity, the Earth orbits the Sun. Maybe Aristotle was right after all. The answer is not easy, and it took Einstein almost a decade to work out the details. The result, published in 1916, is the general theory of relativity, which is often cited as the most beautiful scientific theory of them all. General relativity is notoriously mathematically and conceptually difficult when you get into the details of making predictions that can be compared with observations. Indeed, most physics students in the UK will not meet general relativity until their final year or until they become postgraduates. But having said that, the basic idea is very simple. Einstein replaced the force of gravity with geometry, in particular, the curvature of space and time. Imagine that you are standing on the surface of the Earth at the equator with a friend. You both start walking due north, parallel to each other. As you get closer to the North Pole, you will find that you move closer together, and if you carry on all the way to the pole, you will bump into each other. If you don't know any better, then you may conclude that there is some kind of force pulling you both together. But in reality, there is no such force. Instead, the surface of the Earth is curved into a sphere, and on a sphere, lines that are parallel at the equator meet at the pole. They are called lines of longitude. This is how geometry can lead to the appearance of a force. Einstein's theory of gravity contains equations that allow us to calculate how space and time are curved by the presence of matter and energy, and how objects move across the curved space-time, just like you and your friend moving across the surface of the Earth. Space-time is often described as the fabric of the universe, which isn't a bad term. Massive objects such as stars and planets tell the fabric how to curve, and the fabric tells objects how to move. In particular, all objects follow straight-line paths across the curved space-time that are known in the jargon as geodesics. This is the general relativistic equivalent of Newton's first law of motion. Every body continues in a state of rest or uniform motion in a straight line unless acted upon by a force. Einstein's description of the Earth's orbit around the Sun is therefore quite simple. The orbit is a straight line in space-time, curved by the presence of the Sun, and the Earth follows this straight line because there are no forces acting on it to make it do otherwise. This is the opposite of the Newtonian description, which says that the Earth would fly through space in what we would intuitively call a straight line if it were not for the force of gravity acting between it and the Sun. Straight lines in curved space-time look curved to us for precisely the same reason that lines of longitude on the surface of the Earth look curved to us. The space upon which the straight lines are defined is curved. This is all well and good, but there may be a question that's been nagging away in your mind since I told you that the ground accelerated up and hit the feathers and the bowling ball at Plum Brook like a cricket bat. How could it possibly be that every piece of the Earth's surface is accelerating away from its center, and yet the Earth stays intact as a sphere with a fixed radius? The answer is that if a little piece of the Earth's surface at Plum Brook were left to its own devices, it would do precisely the same thing as the feather and the bowling ball. It would follow a straight line through space-time. These straight lines point radially inwards towards the center of the Earth. This is the state of rest, if you like, the natural trajectory that would be followed by anything. The geodesics point radially inwards because of the way that the mass of the Earth curves space-time. So a collapsing Earth would be the natural state of things without any forces acting, one in which ultimately all the matter would collapse into a little black hole. The thing that prevents this from happening is the rigidity of the matter that makes up the Earth, which ultimately has its origin in the force of electromagnetism and a quantum mechanical effect called the Pauli exclusion principle. In order to stay as a big, spherical, Earth-sized ball, a force must act on each little piece of ground, and this must cause each little piece of ground to accelerate. Every piece of big spherical things like planets must continually accelerate radially outwards to stay as they are, according to general relativity. From what I've said so far, it might seem that general relativity is simply a pleasing way of explaining why the Earth orbits the Sun and why objects all fall at the same rate in a gravitational field. General relativity is far more than that, however. Very importantly, it makes precise predictions about the behavior of certain astronomical objects that are radically different from Newton's. One of the most spectacular examples is a binary star system known rather less than poetically as PSR J0348 plus 0432. The two stars in this system are exotic astrophysical objects. One is a white dwarf, the core of a dead star held up against the force of gravity by a sea of electrons. Electrons behave according to the Pauli exclusion principle, which, roughly speaking, states that electrons resist being squashed together. This purely quantum mechanical effect can halt the collapse of a star at the end of its life, leaving a super-dense blob of matter. White dwarfs are typically between 0.6 and 1.4 times the mass of our Sun, but with a volume comparable to that of the Earth. The upper limit of the mass of a white dwarf is known as the Chandrasekhar limit, and was first calculated by the Indian astrophysicist Subrahmanyan Chandrasekhar in 1930. The calculation is a tour de force of modern physics, and relates the maximum mass of these exotic objects to four fundamental constants of nature: Newton's gravitational constant, Planck's constant, the speed of light, and the mass of the proton. After almost a century of astronomical observations, no white dwarf has ever been discovered that exceeds the Chandrasekhar limit. Almost all the stars in the Milky Way, including our Sun, will end their lives as white dwarfs. Only the most massive stars will produce a remnant that exceeds the Chandrasekhar limit, and the vast majority of these will produce an even more exotic object known as a neutron star. In the PSR J0348 plus 0432 system, quite wonderfully, the white dwarf has a neutron star companion, and this is what makes the system so special. If the remains of a star exceed the Chandrasekhar limit, the electrons are squashed so tightly onto the protons in the star that they can react together via the weak nuclear force to produce neutrons with the emission of a particle called a neutrino. Through this mechanism, the whole star is converted into a giant atomic nucleus. Neutrons, just like electrons, obey the Pauli exclusion principle and resist being squashed together, leading to a stable, dead star. Neutron stars can have masses several times that of our Sun,